When we left off last time, we were drawing these shear diagrams, V of x, and moment diagrams, M of x. And these diagrams were telling us for a beam whose coordinate x goes from 0 at the left end to L at the right end, if you cut the beam somewhere, section it, what force, V, and what torque, M, does one side of the beam have to exert on the other to keep both sides in equilibrium. One point that we made earlier that we can make again now is if I have two sides of a beam and a section here, the near end needs to exert not only a force but also a torque to hold up the far end. You can see, here I am, the near end, I'm exerting a force on the far end. That's enough to keep it from falling to the ground, but it's not enough to keep it straight or nearly straight. To keep it straight or nearly straight, to keep it from pivoting like this, I need a torque, and that torque is provided by in the case of a cantilever, the tension in the upper fibers and the compression in the lower fibers. We said that this shear diagram V is the running sum of all forces up minus down acting on the beam from 0 up to and including x. So that's how you get V as a function of x. You can also notice that if you have a distributed load W, a positive value of W really means a downward force on the beam. So this shear diagram V is minus the integral of W with offsets on both sides for the support forces. Then this moment diagram M equals the integral of the shear diagram V. And when you integrate, there's a constant of integration, and that constant of integration is determined by what's happening at the ends. Usually at the end there is 0 torque or moment, though an exception to that is the end of a cantilever that is attached to a wall, since that attachment to the wall of a cantilever can and does exert a torque or moment on the beam at the point of attachment. That took a while for us to wrap our heads around, and then as if that weren't complicated enough, I said we can integrate this M curve one more time, and we will get something which turns out to be the slope of the tangent line of the beam with respect to horizontal as a function of x. And then if you integrate that one more time, you get the deflection of the beam with respect to the original unloaded flat orientation as a function of length x along the beam. So if you have a beam which is supported on both ends and is uniformly loaded, you expect a shape like this. And if you have a beam which is a cantilever that's loaded at the end or is uniformly loaded, then you expect a shape like this. We also said earlier that the stiffness of the beam is proportional to this second moment of area, which for example distinguishes a plank from a joist. And we said that we would later show that the deflection is inversely proportional to that second moment of area, I, but we just said it, we didn't prove it. So we want to use some math and some geometry to argue why these statements are true. Earlier you read a Giancoli chapter and you noticed that if a person stands on a diving board, then the top surface of the diving board is in tension, it gets elongated, and the bottom surface of the diving board is in compression, it gets squished. And so we can sort of make that same effect here with this piece of foam. So I start out with lines that are forming a nice rectangular grid, and if I apply a bending moment to the two ends, and here I'm bending it into a frown, then you see the bottom is in compression, so you can see the axial strain squishing the bottom, and you can see the axial strain stretching the top. And then if I were to do something similar with a beam that is simply supported, so it's supported on the ends and there's a load in the middle, then you would see the opposite is true, so the top is in compression and the bottom is in tension. We draw pictures that look more like this shape. You could kind of imagine this for a cantilever. This shape where it's frowning but both sides are sagging downward seems a little bit contrived, but it turns out to be a nice shape for drawing diagrams. So we'll draw diagrams that look like this. Now you know the bottom of this piece of foam is being squished, it's in compression. The top of this piece of foam is being stretched, it's in tension. So you can imagine that somewhere in between the part which is squished and the part which is stretched, there is a part which is neither squished nor stretched, because you go, more and more up, you get more and more stretched. You go more and more down, you get more and more squished. So somewhere in the middle there must be a place which is neither squished nor stretched. So that is called the neutral surface. So the neutral surface, if you have a uniform material and a rectangular cross-section, then the neutral surface is right through the middle. If you have a uniform material, the neutral surface will be through the centroid. And many textbooks, Onouye's included, include some drawings that show how the history of thinking of what happens to a piece of material when you load it like this. For a long time the thinking on this topic was incorrect. It took a while for people to understand that in fact there is a neutral surface in the middle, and then in a situation like this the bottom is in compression and the top is in tension. And another thing you can notice is we start out with all these vertical lines parallel to one another, and those lines remain lines, but now you see if I bend this to a significant degree, then those formerly parallel lines now seem to converge towards some center. So they kind of become rays that emanate out from a point. So let's see if we can analyze that. So Navier's hypothesis is that sections that are originally plane and parallel remain plane after bending, but they converge onto a common center of curvature. Okay, and actually a rubber beam does an even nicer job than my foam beam at illustrating this. So here's a nice illustration of a rubber beam on the top in its non-flex state, where you have this nice rectilinear grid drawn on it, and then in the bottom in its curved state, so there is a bending moment applied to it. It's being bent into a circular arc, and you can see that the previously parallel lines that are vertical on this green piece of foam, if we bend the green piece of foam into a circular arc, then those lines all converge onto the center of curvature. So that hints at how we can use geometry to argue how the strain, that's the amount that the material is squished or stretched, changes as a function of how far we are away from that center of curvature. This little model of a beam is intended to reinforce the idea that for a cantilever, for a beam which is frowning, the top is in tension and the bottom is in compression. So we have three springs here. This one will basically represent our neutral surface, and this will represent the top surface, and this will represent the bottom surface. Notice we have all these vertical colored stripes, and there is a black stripe that you can't see right behind this edge. Now if we move this over past the end of the table, then you will see that our neutral spring in the middle basically stayed the same length. So you see it's not really stretched or compressed. It's lined up still with the black tape. The top, which is in tension, is longer, so it's beyond the black tape. And the bottom, which is in compression, is shorter. So it is shorter than, it doesn't reach the black tape, and it almost doesn't reach the green tape even. So this is a nice demonstration, again, that we have for a cantilever, we have tension on the top, compression on the bottom. We've said many times now, if I bend a beam into a frowning shape, we have tension on the top, compression on the bottom. These lines, which start out parallel, perpendicular to the beam axis, parallel to one another, bend, and if I were to bend the beam into a circular arc, then I should get a pattern that looks like lines that converge to the center of the circular arc that the beam curves into. You can see they get closer on the bottom, they get farther on the top. You can also see from the part that's curving the most here, again, that the strain is larger the farther away you are from the neutral surface. And then I could instead bend this into a smiling shape, and then you see that I have compression on the top and tension on the bottom. We want to relate the shape of a beam when it bends under load to the strain and the stress in the fibers that we imagine constitute a beam, that really do constitute a wooden beam, and that we sort of imagine are there for the purposes of envisioning stress and strain in other materials. And we want to relate those internal stresses to the bending moment and the shear force that we drew as V and M diagrams last time. And the reason we want to do this is so that we can relate both the shape that a beam takes under load and the internal stresses within a beam to the weight that we put on top of a beam, to the load that a beam is designed to bear, so that we can understand why some tasks seem to require beams of one dimension and other tasks seem to require beams of another dimension. And in doing this, we want to connect the physics of what's happening inside a piece of material to the real world observation that you can look around the basement of a house and ask yourself, why do the various members have the size they have? So when a beam bends into a frowning shape like this, the material on top is stretched, it's in tension. The material on the bottom is compressed, it's in compression. And somewhere along the middle, there is a neutral surface whose length does not change. In this diagram, we've drawn the x-axis to be along the neutral surface, and this neutral surface is defined by the variable y equals 0. So we're saying y equals 0 is the neutral surface. Y is going upward. Y is also the direction in which gravity acts. So we're accustomed to looking at the weight loaded onto a beam by looking at an xy view. We said x was the variable we typically use to describe the length of a beam, the axial coordinate going from one end to the other. So this would be the x-axis going from one end of this hypothetical beam to the other. The y-coordinate is vertically upward in this case. So Navier's assumption is that when you bend a beam, there is a neutral plane whose length does not change. That neutral plane can be bent into a circular arc, an arc which is a portion of a circle. And these surfaces of constant y, here's y equals 0. Here's the very top surface, which we were calling y equals plus h over 2 when we looked at cross sections. Here's the very bottom surface, which we were calling y equals minus h over 2 when we looked at cross sections. Those surfaces will also bend into circular arcs. So the top surface will bend into a circular arc of larger radius, and the bottom surface will bend into a circular arc of smaller radius. And I think you can see that for this top portion of this foam beam. You can see one circle, another circle, another circle, another circular shape. And then you can see that the lines, which initially were vertical, have become radial lines, but they're still lines. So these lines are still lines, but now they are radial lines. These planes that we could cut perpendicular to the axis of the beam remain planes, but they become radial planes. So this is constant x, constant x, constant x. So these surfaces of constant x are still lines, but they're no longer parallel to one another. Now they are radial lines emanating out from this point to which all of these radial lines converge. So this x-axis bends into the arc of a circle of radius r, and then up here at y equals plus h over 2, so this y equals plus h over 2 bends into an arc of radius r plus y, so that's r plus h over 2, and this lower line, which corresponds to y equals minus h over 2, bends into a circular arc of radius y equals r minus h over 2. If we take this orange interval, whose initial length is L0, along the neutral surface, its length still equals L0. Up above the neutral surface, for this frowning shape, its length is bigger than L0. Down below the neutral surface, its length is smaller than L0. And by using the fact that these are circular arcs, we can see exactly how much bigger than L0 this is and how much smaller than L0 this is by taking these surfaces of constant y to be circular arcs with the same center. So if this distance from the common center is r up to the y equals 0 plane, then this distance up to the top surface of the beam must be r plus h over 2. And in general, for some value y, this distance must be r plus y. Y is bigger than 0 up here, y is smaller than 0 down here. Then, if we call this little wedge angle theta measured in radians, then we know what this L in the middle is. This L equals r theta. So if we measure the angle in radians, we can just get the arc length as the radius times the angle measured in radians. And then we don't have to just say this is bigger than L0. We can say this new length is r plus h over 2 theta, and this is r minus h over 2 theta. And in general, if we have a distance y above the neutral surface, then this new arc length is r plus y times theta. So we had a small circular arc of initial length L0, which equals r theta, has length L equals r plus y theta after bending. That tells us that the strain is the change in length divided by the initial length. So we can easily work out the strain from the ratio of the original length and the new length. So the strain, I'll use little e. I think Onouye uses lowercase epsilon. This is L minus L initial divided by L initial. So that would be r plus y theta minus r theta over r theta, and the theta cancels out. And what's left is y over r, which is the height above the neutral surface divided by the radius of curvature. And again, to get that, we said that the neutral surface is bent into a circular arc of radius r. So if you say it's a circular arc, that circular arc has some radius, so r is just what that radius happens to be. And you say, okay, these other surfaces of constant y form concentric circular arcs. So if the radius of this arc is r, then the radius of this arc at a height y is r plus y. And at the maximum value of y, it's r plus h over 2. At the minimum value of y, it's r minus h over 2. Another way to see this same result is to draw a vertical line that intersects this radial line at the neutral surface. So this green line was initially vertical, but now it is at an angle. And as a result, this is the same length, but this has become longer and this has become shorter. So it's this sort of wedge-shaped piece which describes the added length up above the neutral surface and the subtracted length down below the neutral surface. And so this little magenta piece is the length added up above, or this little magenta piece is the length subtracted down below. And you can notice that this green line's angle with respect to the vertical is the same as this green line's angle with respect to the vertical. And so this little change in length divided by y, right, y is how far up above the neutral axis we are, is the same ratio as the original length divided by r. So that's kind of a similar triangles way to see it. You say this little added length divided by y equals this original length divided by r, which gets you to the same end result. If you wrote that down, we would say delta L divided by y equals L initial divided by r, which gives us delta L over L0 equals y over r, maybe more directly. And we did that by looking at this little wedge and this little wedge. Moving over to this vertical green line to give us some space to work, we see that this is most stretched, this is a little less stretched, this is a little less stretched, this is a little less stretched, this is barely stretched at all, this is barely squished at all, this is a little more squished, this is a little more squished, this is more squished, most squished. So we have nothing here, bigger and bigger and bigger tension, nothing here, bigger and bigger and bigger compression. So the tension gets bigger and bigger in a linear fashion as we go up from the neutral axis, and the compression gets bigger and bigger in a linear fashion as we go down from the neutral axis. Sometimes you'll hear me say neutral axis instead of neutral surface. If you're looking through one slice of the beam, then the surface becomes an axis. So sometimes people say neutral axis instead of neutral surface. It's more correct to say neutral surface. So we know this material is the most stretched and this material is the most squished. That's a strain. That's the change in length. Now let's turn that into a description of the forces. You imagine that we have little fibers running running through the length of the beam, as we really do in a wooden beam, but we can kind of imagine that it's there even in beams of other material, then let's try to ask what is the tension in this fiber up here, or what is the compression in this fiber down here after the beam is bent. So remember, Hooke's law tells us that in the linear elastic region of the material properties, we have stress, little f, is proportional to the strain, little e, and the constant of proportionality, big E, is Young's modulus. So we have an expression for the strain, so we can just plug this Hooke's law into this expression for the strain, and we can say that the stress equals Young's modulus times y over r, since the strain is y over r. So remember, the stress is force per unit area, so the force per unit area equals Young's modulus times our height up above the neutral surface divided by the radius of curvature that we've bent the neutral axis of the beam into. Now let's pick a fiber going along the length of our beam. So we're going to pick a fiber up here at some height y above the neutral surface, and so on this bent beam that fiber will be up here, and here is the height y above the neutral surface. And then we can look in this other projection. So we've been looking at the y versus x, and then here is the bent into a circular arc x, and we have these radial y values. If you look at this kind of three-dimensional image of the beam, here's x running along the length of the beam, and here's y going upward perpendicular to the axis of the beam and opposite the way gravity points in the unbent beam. Usually the load that we apply on the beam is in the negative y direction. So we also want to acknowledge that this beam has a third dimension. In this context, I will call that third dimension z, since we're already using x and y. Let's call it z. It's a little bit confusing because chapter 6 on cross sections called the two axes that I'm going to call z and y, it called them x and y, but we're already using x in this context, so we really need a new name. So let's say what chapter 6 called x, we're going to call z here. So z is the width of the beam axis, and y is the height of the beam axis, and then x is the length of the beam axis. That could be worth writing down. So we'll take x to point along the length of the beam, whether it's not bent or it's bent. We'll take y to point along the height of the beam, whether it's not bent or it's bent. So in the bent form, y is radial, and in the bent form, x is circumferential. And then we'll take z to point along the width of the beam. So the xy plane is where we draw our beam loading diagrams, and the xy plane is also the plane where the bending happens. And the yz plane is the plane of the cross-section of the beams. And we're talking about the second moment of area for making a stiffer beam by shaping the material differently. That is this end view, the cross-section view we're talking about. So for now, let's call that the yz plane. So here's y going up along the height direction, and here's z going along the width direction. So if I want to pick out one little fiber, I want to pick out one little spot of area in the middle of the cross-section. I mean, really, I want to evaluate across the entire cross-section, but we're going to use calculus, and we're going to go one little infinitesimal chunk at a time. And this chunk will be a height y above the neutral surface. So here we have y is how high up this chunk is. And we're also going to say that this little chunk has an area dA, where we use little d in the calculus sense to mean it's an infinitesimal, and we're going to add up all of these little chunks by integrating using calculus. Here's this fiber running along the length of the beam, and I'm going to give that fiber a cross-sectional area dA. And then here's that same fiber running along the length of the bent beam, and it still has this cross-sectional area dA. I want to know what is the tension in this little fiber. Well, the tension in that little fiber is just the force per unit area times the area. So the tension in this fiber that runs along the beam axis is a force, so that's force per unit area, which is this stress, times the cross-sectional area of that fiber, which is this little infinitesimal area dA. That is, force per unit area is stress, and this cross-sectional area is dA, and I'm going to call this infinitesimal tension, and it could be a compression below the neutral axis, it's a tension above the neutral axis. I'm going to call it dF, an infinitesimal force. Okay, so it'll be a positive dF for tension, and it'll be a negative dF for compression. And then we can plug in the expression we already have for the stress. So that expression we already have for the stress, the force per unit area, is Young's modulus times the height above the neutral surface divided by the radius of curvature. Okay, so the tension, if positive, or compression, if negative, in this little fiber that has cross-section area dA is the stress, which is given by this expression, times dA. So that tells you how big a force this little fiber contains, like its tension or compression. And what we really want to know is the torque, because we want to relate this to the bending moment. So we want to relate how much the top of this beam stretches, how much the bottom of this beam squishes, to how big a torque has to be exerted within the beam. If I cut the beam here and I say how big is the torque that one side exerts on the other side of this section, that's the bending moment. I want to relate that to how much the top stretches and how much the bottom swishes. To do that, I am going to use this point along the neutral surface as my pivot. So this is my pivot at the neutral surface, and then I have a force up here which points one way for tension and the other way for compression. But either way, if we have tension above or compression below, either way I get the same sense of the torque. So I will add up all these contributions to the torque. So the torque, which we call a moment in architecture or engineering, due to this fiber is, so here's a little differential of torque we're calling dm. So this is a lever arm times the force. The lever arm, since this force, whether it's compression or tension, points in the axial direction, the lever arm is perpendicular to the axial direction. So the y-axis is perpendicular to the axial direction. So the lever arm is just y, the distance above or below the neutral surface. And then we can use this expression for df along with y, and we get y times e times y over r dA. So this is pretty important, but let's rewrite it where we have more space. Okay, so the bending moment due to this tension, and it will just be an opposite sign contribution if it's compression, is dm equals y e y over r dA, which equals e over r y squared dA. Then we're going to integrate this to add up over all of the little chunks of cross-section in the beam. So we said, thanks to the geometry of concentric circles, that strain, little e, is y over r. Y is the height above the neutral surface, r is the radius of curvature into which we bend the neutral surface of the beam. We plugged in Hooke's law, stress equals Young's modulus times strain. That gave us that the stress was Young's modulus times y over r. That then, by multiplying by the area of this little fiber, gave us the tension in one of these axial fibers. That is Young's modulus times the height above the axis divided by the radius of curvature times the differential area, the little infinitesimal area of the fiber in cross-section. Then multiplying by the lever arm, and the lever arm, since this force is axial, we want the lever arm perpendicular to the axial direction. Perpendicular to the axial direction is this height y above the neutral axis, since we're using this point along the neutral surface as our pivot. So this infinitesimal torque, or bending moment, is just y, the height above the neutral surface, times this infinitesimal tension in the fiber, which itself is just Young's modulus times y over r times the little chunk of area. Now we can add up all these little chunks of area to get the bending moment, which is when you bend the beam, if you were to cut the beam here, you want to ask what is the torque that one side of the beam exerts on the other side of the beam to resist this bending. So the bending moment is m equals the integral of dm, which is the integral of e over r y squared dA. We can take the constants out. So this bending moment, which is the torque that one side of the beam exerts on the other when we section it here, is e over r integral y squared dA, which is e over r times our old friend I, the second moment of area. So this is really interesting because we were wondering, why the heck do we care about this second moment of area, integral y squared dA, for the cross-section of the beam? And now, suddenly, this integral y squared dA has appeared in our analysis of how do we figure out what torque half of the beam exerts on the other half of the beam when we bend the beam. So if we bend it, and then we use a section, a cut right here, to analyze what's one side doing to the other to hold it into equilibrium, we can say, okay, what's the torque exerted by one side on the other? To figure out that torque, we have to figure out all of the little forces, and we have to multiply each little force by its corresponding lever arm. Its corresponding lever arm equals how far up above the neutral surface is it. And then what that individual force is, multiplied by the lever arm to get the torque, what that force is the stress in this fiber times the cross-sectional area of this fiber. And the stress is just proportional to the strain by Hooke's law, and the strain is proportional to how far away from the neutral axis I am, because the surfaces of constant y bend into a sequence of concentric circles, and the concentric circles that are up higher are of larger radius and therefore larger circumference, and the concentric circles that are down lower are of smaller radius and therefore smaller circumference. So this mysterious sum, the second moment of area, the sum or the integral of y squared dA, which is what distinguishes this beam shape from this beam shape from this beam shape, for example, has appeared here when we try to connect the forces and torques inside the beam to the deflected shape of the beam. And it's worth going back to ask, why are there two factors of y here? I always found this mysterious. Why is it y squared dA? Where do the two different y's come from? One y comes from the fact that the strain is proportional to how far up you are from the neutral surface. So the farther away you get, the bigger the strain is, and the stress is proportional to the strain. The other factor of y comes from turning that force into a torque. To turn that force into a torque, you multiply by a lever arm, and if we're pivoting about the neutral surface, then the fibers farther away from the neutral surface have a bigger lever arm. Not only is there a bigger tension in the farther away fibers because the strain is bigger, but there's also a bigger torque because we're farther away from the neutral surface and therefore we have a bigger lever arm. So that's sort of the neat thing about where the two factors of y come from in y squared dA. One of them comes from strain, how much it's stretched, being proportional to how far I am from the neutral axis, and the other comes from multiplying a force by a lever arm to get a torque, and the lever arm is how far up I am from the neutral surface. We have here a really simple model of a beam. This bolt serves as a pivot, so you can see everything else is pivoting around this one bolt that my finger is resting on. Each half of this beam is sort of sectioned here. Each half of this beam is a little piece of pegboard, and then over here I have 4 rubber bands attached to 4 pairs of bolts, and 4 rubber bands are respectively 1.5, 3.5, 4.5, and 5.5 pegs above the pivot. You can see the pivot is in between 2 pegs here. I have a little weight on here now just to counteract the force exerted by these rubber bands to keep this initially approximately unbent. If I increase the load on this end of the beam, then somehow about this section there will be a torque exerted by one side on the other, and this seems to me a slightly less abstract way to see how that looks. So I'll put a little bit of weight here, and you can see now that the top half of this beam is in tension, the bottom half of this beam is in compression. And one thing that stands out right away, if you look at this pencil mark, which a moment ago was vertical, is that the strain, which is how stretched each rubber band is, or how stretched the fibers of the beam are that are being represented by these rubber bands. So the strain is proportional to the distance above the neutral axis. And then you can't see it down below, but it's easy to imagine that down below the compression is likewise proportional to how far below this pivot we are. So this pencil mark is initially vertical, and then as I apply a load to the end of the beam, the top goes into tension, the bottom goes into compression. And then what the pencil mark makes intuitive here is that the strain of these fibers of the beam, a distance y above the neutral surface, is proportional to y. So the farther up you are from the neutral surface, the larger the strain, and in a proportional way, since this is just a triangle. So the strain is proportional to how far you are above the neutral surface for a beam that is frowning, and if the beam were smiling, it would be the other way around. The bottom, the strain would be proportional to how far we are below the neutral surface, and the top would be in compression. But we've built this model so that it frowns rather than smiling. So the top is in tension, the bottom is in compression, and you can imagine that this rubber band is stretched the most and this rubber band is stretched the least. And then if each rubber band were a Hooke's law spring, then the force exerted by each rubber band would be proportional to how stretched it is. So statement 1 is that this strain is proportional to how far up we are above the neutral surface. Statement 2 is that the stress is proportional to the strain. That's Hooke's law. That means that the force exerted by each little fiber is proportional to how far up that fiber is from the neutral surface. Then, using this point along the neutral surface as a pivot, you can see that the corresponding torque is proportional to this force times the distance above the neutral surface, since the distance up from the neutral surface is perpendicular to the direction of this force. So the lever arm equals the distance above the neutral surface. So the force in each fiber, the tension in each fiber, is proportional to how far up that fiber is from the neutral surface, and there's an additional factor of how far up we are from the neutral surface to turn that force into a torque. So that's 2 factors of y, this distance above the neutral surface. One for how stretched things are, this geometrical triangle shape, and a second for the lever arm to turn this force into a torque. So the contribution to the torque about this pivot from a fiber a distance y above the neutral surface is proportional to y squared. And that's the key point I wanted to try to illustrate for you about the origin of this mysterious expression, the integral of y squared dA, or the sum over all little fibers of y squared times the cross-sectional area of that fiber. That's like the sum of y squared times delta A, where delta A is the cross-sectional area perpendicular to the axis of the beam of each little fiber that we envision. So we add some weight down here on the end of our cantilever. That creates a moment which is trying to bend each section of the beam, but we only made this one section flexible. In a real beam, the entire length is flexible, but we're just focusing on this one little section, so we made it flexible. You can see that the strain in the fibers is proportional to how far up we are above the neutral surface, and you can see that the beam bends more and more until finally the torque created by these fibers that are being stretched balances the torque created by adding this weight. And if I subtract this weight, then a smaller torque is needed internally to counteract that, and therefore each fiber stretches less, producing a smaller Hooke's law force. And then I make the load larger again, and we get a clockwise torque caused by this weight, and then there's an opposing counterclockwise torque caused by this tension. In a real beam, there would also be a counterclockwise torque caused by this compression, but we don't have any springs here in compression to illustrate. So in real life, there would be both fibers up here in tension and fibers down here in compression. So again, we're trying to illustrate why it makes sense intuitively that the beam stiffness should be proportional to this mysterious expression, the integral of y squared dA. Or if you don't like calculus, we can call it the sum of y squared delta A over all little patches of the beam cross-section. Next, I can remove these rubber bands and replace them with just a single force measuring device. So I have this Newton scale which measures from 0 to 50 newtons. And let me first attach it up here at the bolt, which is 5.5 pegboard spaces above the pivot. And it seems as if the required force to keep everything balanced is about 10 newtons. That's applying it up here with a lever arm of 5.5. Let's go down to a lever arm of 3.5 and see what that corresponding force looks like. I predict it should be bigger by a factor of 5.5 to 3.5 because I'll need a bigger force at this smaller lever arm to produce the same torque. So now we have a force of about 15 newtons, which actually makes sense because the ratio of 5.5 to 3.5 is about 1.6, so we'd expect about 15 or 16 newtons. And now we can move down to this 1.5 peg mark space, and the ratio of 5.5 to 1.5 is about 3.7, so I think we expect about 37 newtons now if we move down to the 1.5 pegboard location. Well, it seems like something's a little bit off in my calculations. I only get about 30 newtons when I thought I would get more like 36 newtons, but qualitatively it's still not bad. Let me try it again with these little weights removed so I don't need quite so big a force. So now we just have the weight of the pegboard itself. So here we are at 1.5 pegs above the pivot, and this is a force of about 18 newtons. And then if I move from 1.5 to 4.5 pegs above the pivot, I think it should be 1/3 that force. Let's see how this works out. And that's pretty good. So that's about 6 newtons. So that is about 1/3 of the 18 newtons we measured before. So we were at 1.5 pegs, we got about 18 newtons. And then 4.5 pegs, which is 3 times the lever arm, we have about 1/3 the force, about 6 newtons. I guess that shouldn't be too surprising. I'm just showing you that, maybe unsurprisingly, the torque is indeed proportional to the lever arm. So we have the force times the lever arm equaling the torque. But I'm trying to illustrate for you that a force applied a distance y above the neutral surface indeed produces a torque, a bending moment, proportional to that height y above the neutral surface. Okay, now let's see what else we can do with this relationship. One thing we can do right away with this result is turn it upside down and solve it for the radius of curvature, and we get that the radius of curvature equals Young's modulus times the second moment of area divided by the torque that you apply. And this actually makes some sense. If I apply a bigger and bigger and bigger torque to try to bend this meter stick, then it bends into a smaller and smaller radius. It's a little bit hard for me to do too much of that with this meter stick, but I can also do it with this piece of foam. And you can see that as I apply a bigger and bigger torque, it bends into a smaller and smaller radius of curvature. Or with this other piece of foam, as I apply a bigger and bigger and bigger torque, it bends into a smaller and smaller radius of curvature. So I think it makes sense that there's an inverse relationship between the radius of curvature and the torque, the bending moment that I apply. You can also imagine in your mind's eye what would happen if I used a stiffer material. So if I use a stiffer material with a larger Young's modulus, then for the same torque, I'm going to get a larger radius of curvature because, more curved means smaller radius. So right now the radius of curvature is infinite, and then I'm making the radius of curvature smaller and smaller and smaller. If I were to apply the same torque to a less stiff material, I'd get a smaller radius of curvature. It would bend into a tighter circle. And then you can even see the result of trying to bend this material this way versus this way. That's like this way versus this way. Okay, so on end versus on the flat. So if I try to bend this meter stick like this, there's a pretty small value of I, the second moment of area, when I put this ruler on the flat. The same ruler, I put it on end, and I've made the second moment of area about 10 times as big. And you can see that it is much more difficult. Here it's not too difficult. Here it's much more difficult for me to bend it. So the radius of curvature into which I'm able to bend it with a given torque is much bigger when I orient it with a larger I value. When I orient it with a smaller I value, then the radius of curvature I get for a given torque is smaller. That makes sense. It's bent into a tighter circle, smaller radius of curvature. So I think we can already get some intuition from this expression. I have here 3 different meter sticks. Let's look at these 2 first. So these 2 meter sticks are of, one is plastic, the white one is plastic, the one that's wood color is wood, and you can see that their cross sections are very similar, if not identical. Okay, so they seem to have the same cross-sectional shape and size. So what differentiates them is that their 2 materials have very different Young's moduli. So we worked out on the light board that the radius of curvature of an object when you apply a bending moment, so bending moment is a torque. So if I apply a torque to the 2 ends of this meter stick, then initially it's a straight line. A straight line has infinite radius of curvature. So it's not curved. Its second derivative is 0. So the radius of curvature, which is inversely proportional to the second derivative, is infinite, since the reciprocal of 0 is infinity. So if I apply a bigger and bigger bending moment, that's a bigger and bigger torque, then this bending moment is downstairs. It bends into a smaller and smaller radius of curvature. I don't want to bend it too much or it will snap. Now when you look at the cross section of this meter stick, you can see that it is about 3 or so times taller than it is wide. It depends on which way you orient it. And we mentioned when at the light board that the ratio of this second moment of area to this second moment of area equals the square of this aspect ratio. If this aspect ratio is about 3 or so, then the square of this aspect ratio is about 10. So that tells you if I apply the same torque this way versus this way, then it should flex about 10 times more this way than this way. And in fact, this radius of curvature for the same torque should be about a tenth of what this radius of curvature is for that same torque. Now you can see if I apply a kind of, medium-sized torque, the radius of curvature that this bends into. So let's try it with the wood, which has a larger Young's modulus than the plastic. So same cross-section, but larger Young's modulus, E, and you can see that the radius of curvature that we get is much larger. In other words, it flexes less. In other words, it stays straighter, because a tighter curve means a smaller radius of curvature. If it's more curved, that's a smaller radius of curvature. If it's more straight, that's a bigger radius. So something that's a straight line has an infinite radius of curvature. If it's curved into a really tight loop, that's a very small radius of curvature. Okay, so I'm trying to apply about the same size torque to this wooden beam, and you can see it's not curving as much. So this is a bigger radius of curvature. If it curves less, that's a bigger R. And if I turn it on its end, so now I'm also making the I factor, the second moment of area factor, be bigger, then you really can't even see it curve at all. So I try pretty hard to bend it, and there's no noticeable curve. By contrast with the plastic one held on end, I can still produce a noticeable curve even when it's on end. And then when it's on the flat, I can produce a very noticeable curve. Okay, so that is the effect of the E, Young's modulus, and I, the second moment of area, for a given. I'm trying to apply about the same bending moment, about the same torque each time, and we're seeing the effect on the radius of curvature. I have one more example beam. This is also plastic, but you can see this is a box beam. So it has material in a square pattern around the outside, and then the inside is empty. That's a so-called box beam. And so it's plastic, so it doesn't have the benefit of the very large Young's modulus, but you can see that it is pretty difficult for me to bend. I guess if I compare it to this, it seems as if this box beam shape is less stiff than the plastic when it's on end, but it's more stiff than the plastic when it's on the flat. So this is also plastic. Yes, it seems as if this box beam configuration must have a second moment of area, which is bigger than this, but smaller than this. There's another really useful result we can get at this stage. So we wrote down earlier that the stress in a fiber that runs along the axis of the beam equaled this Young's modulus times how far up am I from the neutral surface divided by the radius of curvature of the beam. And we have an expression here for the radius of curvature of the beam. So let's plug this expression for the radius of curvature of the bent beam into this expression for the stress, and we can figure out something about how to relate the axial stress inside the beam to, for example, the bending moment. So I'll take that the stress, little f, is Young's modulus times how far up y am I from the neutral surface divided by r, the radius of curvature, and then I'll plug in this expression for the radius of curvature. So this is E y over, okay, here's this expression, E I over m, and we can then do some rearranging. So this seems like y stays on top. We have m is in the denominator of the denominator, so that goes into the numerator, and the elastic modulus cancels. So that gives us that the axial stress, that is, how much force per unit area does each little fiber composing the beam have to bear? It is proportional to the bending moment. So now you see why we drew those M diagrams, because the place where the internal axial forces trying to snap the fibers of the beam apart or trying to crush the fibers of the beam like a cardboard box, those internal stresses are proportional to the bending moment. So that's why that M diagram is useful, the bending moment diagram. And then we can see that those internal stresses are biggest where we are farthest from the neutral axis. That's not surprising because we saw that the strain is biggest when we're farthest from the neutral surface, and the stress should be biggest where the strain is biggest. And then there's this interesting fact that down in the denominator we have this second moment of area. So when you ask how much force per unit area do these fibers have to bear when we bend the beam, there is this capital M, the bending moment, which is related to how long is the beam and how much weight did we put on it. And then we have this purely geometrical factor, which is how high up am I above the neutral surface and what is the second moment of area. And in fact, if you say, what is the maximum axial stress? So in other words, where is this worse? We would just plug in a value where y equals h over 2, the half height of the beam. So we have that the axial stress is little f is the bending moment times how high am I above the neutral surface divided by the second moment of area, and the maximum axial stress, that is where the bending moment is largest in absolute value, and then times where the distance above or below the neutral surface is largest in value, and then divided by this second moment of area. And that's useful because you don't want the maximum axial stress that fibers in the beam have to bear to be larger than the strength of the material you're working with. Now there's a kind of obscure point here, which I hesitate to mention, but it is in the book. This factor, M maximum relates to how you're using the beam. How long is it? How much weight do you put on it? And where do you put that weight? This factor is purely geometrical. So it relates entirely to the cross-section of the beam that you're using, because a given beam cross-section will have a given height. So this ymax for a rectangular beam would just be h/2, the half height. And then it would have some second moment of area. So the second moment of area and the maximum value of distance that the cross-section can be from the neutral surface are both just geometrical properties of the cross-section. So in fact, any material that one works with will have some allowable maximum stress. So you want the maximum stress inside the beam to be less than the allowable stress. Therefore, you want this bending moment times this geometrical factor, ymax divided by I, to be smaller than the allowable stress for the material you're using. And this expression in parentheses is the reciprocal of a geometrical property of beam cross-sections called the section modulus. This is really obscure. You certainly don't have to remember this, but there's this thing called the section modulus, which is a purely geometrical property of the beam cross-section. And it is the second moment of area divided by the largest value above or below the neutral axis. So this ymax basically is just 1/2 the height of the beam for a symmetric beam shape. Rewriting this up here, that tells you that m max divided by the section modulus has to be less than the allowable stress for the material you're working with. And then you can turn that around, and that tells you that you have to pick a beam whose section modulus is bigger than the maximum bending moment on your m of x diagram divided by the allowable stress for the material that you're working with. So this is a strength criterion in order to prevent the fibers of the beam ripping apart here because the material is not strong enough, or the fibers of the beam from crushing down here because the material is not strong enough. So section modulus turns out to be a property that is tabulated for beam shapes. It might be tabulated for different rectangular beam shapes of gradually increasing depth if you're using lumber, or it might be tabulated for different I-beam shapes as the I-beams become larger and larger. So knowing what material you're working with gives you an allowable stress. And then knowing the largest value of the bending moment from this M diagram, which you know from how you're loading the beam, tells you this numerator. And then the ratio of these two things says, well, I have to look in my table of available beam shapes and pick a beam shape which is larger than this ratio in order to satisfy this strength criterion. That's a little bit of a digression. But while we had this expression written down and while we had this expression written down, it was the appropriate time to bring up that digression. What we're really more interested in is how do we get the shape of the beam once we know what kind of material it's made out of and once we know how much weight we put on it. So that will be the next topic. So next we want to try to figure out what shape the beam takes. So in calculus, there's a relationship between the radius of curvature and the second derivative. And I think you know that. If you have a function whose first derivative is non-zero but whose second derivative is zero, it's just a straight line. So something that curves has to have a non-zero second derivative. So it turns out in calculus the curvature is defined by the reciprocal of the radius of curvature. So it is 1 over r. So that's the reciprocal of the radius of curvature. So if you have a function y as a function of x, it is y double prime of x divided by 1 plus y prime of x squared to the 3/2 power. That's a pretty complicated expression. This is for a function y of x. Okay, so if we have a function y versus x, if the second derivative is 0, it has no curvature. If the second derivative is positive, it's said to have a positive curvature. And if the second derivative is negative, it's said to have a negative curvature. And if we have a small second derivative, not too big in magnitude, then the radius of curvature is pretty big. If we have a much larger second derivative, then the radius of curvature is smaller. So I think that makes sense. We will write capital Y as a function of x for the deflected shape of the beam. So in other words, we initially have a beam which is just perfectly flat, and then we're going to somehow support it like this, and we're going to put some weight on it like this, and as a result of putting that weight on it, it's going to take on some kind of curved shape like that. So I'm going to call this curved shape capital Y as a function of x. I don't want to use little y because we're using little y as the height above the neutral surface. So I'm going to use capital Y just to give us a new variable to work with. So capital Y will be the shape that the beam takes after we put weight on it. So capital Y equals 0, the whole length, would be the original undeflected shape. And then here capital Y is bigger, here capital Y is smaller. So I guess capital Y will kind of become negative in the middle if it's simply supported. Or if it's a, a cantilever, and we have capital Y versus x, it will be something like this. So capital Y will become negative at the far end. So if we have like something that starts out life like this, and then we put a weight on it and it bends into a shape like this, then this will be our capital Y axis and this is our x axis. So this will be a negative value of capital Y. So here we'll have capital Y is less than 0 for the deflected shape of the beam. Okay, so if you just graph the shape that the beam looks like as a function of x, where x is just, again, length along the beam, or original length along the beam, then I'm going to use capital Y for that. Now, in real life, a beam bends a little bit, but not very much. Something that bends this much is very unrealistic. So in a common approximation that is used, and this is an approximation, but it's an approximation that's valid for ordinary circumstances, the approximation that we'll use is that y prime of x in absolute value is much smaller than 1. So this is the small deflection approximation. It's not so much an approximation as a limiting case. So it's kind of like taking just the first one or two terms in a Taylor series. If we assume that the slope of the beam is not gigantic, which is true for anything you would use in ordinary construction, this term goes away and we're left with this is just equal to y double prime of x. So we are going to use capital Y as a function of x for the shape that the beam takes on after it is deflected under load. So if we have this cantilever and we put a big load here at the end and it deflects into some curved shape, then we'll still have y equals 0 at the place where it's attached to the wall, but y will become smaller and smaller and smaller than 0 as we go out farther away from the wall where it's attached, for example. Or if we had a simply supported beam that sort of makes this smiling shape, then this will be y equals 0. This will also be y equals 0, and then down here in the middle we'll have y less than 0. So we want to know what is this mathematical shape that the beam bends into when we put a weight on it. So we will work in this small deflection approximation, which is basically the approximation that this slope dy by dx is always in magnitude much smaller than 1. So we'd never really have this exaggerated shape in real life. You see things bend just a little bit. And in that approximation, we can write that the curvature, mathematicians use the word curvature to refer to the reciprocal of the radius of curvature. So this 1 over r equals, approximately equals, y double prime of x. Okay, so it's the second derivative of the deflected shape of the beam. And so 1 over r is just the reciprocal of this expression. So that is m, and we know that we already know how to write the bending moment as a function of x, and then divided by ei. So the deflected beam shape is y of x. The deflected beam shape y of x is obtained by taking this expression, y double prime of x is m of x over ei, and integrating it twice. You take y double prime, you integrate it twice, and you get y. You have to put in the right constants of integration, though. So we can explore this next. Okay, so to obtain the shape y of x of the deflected beam, we write y double prime of x equals m over ei, and we've already figured out in the previous lecture how to write the bending moment m as a function of x, and then we integrate that twice with respect to x, and that gives us the deflected shape of the beam. You won't actually have to do it, but it helps to see that if this moment diagram is a second order polynomial, a parabola, then the deflected shape of the beam will be a fourth order polynomial. And if this moment curve is a first order polynomial, then the deflected shape of the beam is a third order polynomial, and so on. Okay, so we can write y of x is the integral dx of the integral m of x over ei dx. And usually the material type, which gives you the Young's modulus, and the cross-section are both constant. They don't depend on length along the beam. They're the same everywhere along the beam. So then you can pull the constants out and you get an expression like this. You will never have to use this expression. I will use it once or twice for you to show you where some of these results come from. Normally, what you want to know is what is the largest value of y in magnitude. So if you have a cantilever, you want to know what's the maximum deviation from 0 of the shape of the beam. How far does it deflect at the end? Or if you have a simply supported beam, which then bends into this shape, you want to know how big is this y value in the middle? How much does it sag in the middle compared to being completely flat? So normally all you really care about is the maximum value of this deflection y. You don't care about the exact shape. And these maximum values are pre-calculated and tabulated in tables, and you look them up. But it's always nice to know where something comes from, even if you don't calculate it yourself. So you'll see me do a couple of these integrals just for fun. And if we have to integrate twice, we have to come up with two constants of integration. And the way you'll see me do that, if we have a simply supported beam, which is supported at 2 points, then the constraint will be that y equals 0 at both support points. And if we have a cantilever, which has one end which is fixed to the wall, then at that fixed end of a cantilever, y equals 0 and also y prime equals 0. So we'll get the two constants for a cantilever by saying at the fixed end y equals 0 and y prime equals 0. And we'll get the two constants for a simply supported beam by saying y equals 0 at both ends. In other words, y equals 0 at both places that are supported. So I will do a couple of those examples just for fun, but you don't have to know how to do them. For example, suppose we want to figure out the deflected shape of a cantilever with a single concentrated load on the end. And you remember from the previous video, the shear curve V was the running sum up minus down of all the forces on the beam. So that's just up to plus P on the left side and then back down to 0 on the right. So it just looks like this. And then the moment curve is the integral of this, and it has to be 0 at the free end. And and it can be non-zero at this cantilever fixed end. So this is minus PL over here, and it's 0 over here. There's a positive slope. That makes sense. It also makes sense as a negative value because the beam is frowning. Then we can write an expression for m of x. Okay, so we could say m of x is p times x minus l. So at x equals l, this has the value 0, and at x equals 0, this has the value minus pl. So that seems pretty good. So then we can just use this expression. Okay, so we take this moment curve for the cantilever, which is minus pl at x equals 0, and it's 0 at x equals l. So writing a functional form for that, the moment function is p times x minus l. We can integrate that once to get the first derivative, the slope y prime of x. So I'll factor out the p since it's a constant. P over ei, integrate x minus l as a function of x. So this is x squared over 2. The second term gives us l times x. So there's a constant we have to find. But for a cantilever, the fixed end of a cantilever has 0 slope. So y prime of 0 should equal 0. That tells us that this constant equals 0. So the derivative function, the slope of the beam, is p over ei x squared over 2 minus lx. Then we can integrate once more to get the deflected shape of the beam. So we have x squared over 2 minus lx. We're integrating that. This term gives us x cubed over 6. This term gives us lx squared over 2, and then there's an undetermined constant. But the fixed end of the cantilever has y equals 0, so this constant must be 0. So that gives us y is p over ei x cubed over 6 minus lx squared over 2. So if we plug in x equals l, we get l cubed over 6 minus l cubed over 2. So 1/6 minus a half is minus a third. So that's p l cubed over 3 ei. The minus sign because it's deflected downward. So indeed, if you look it up in a table, the maximum deflection of a cantilever with a point load at the end is p l cubed over 3 ei. So that's sort of neat. We have here our wooden meter stick and our plastic meter stick. And we saw that they have about the same cross section, and they're both on the flat here like planks. So we think that the main difference between these two meter sticks is the Young's modulus. For a cantilever with just a concentrated load at the end, the deflection of the end equals this point load, concentrated load at the end, times the cube of its length, and then divided by, there's a constant that comes out of the math, 3, and then the Young's modulus and the second moment of area. So notice that the Young's modulus and the second moment of area are both downstairs. The weight that you put on the end is upstairs, and then we have the cube of the length. So let's leave the length alone for now, and we have about the same second moment of area for these two meter sticks. I'm going to put the same weight on the end of both of them, but we think they have different Young's moduli, so we'll see that one of them deflects. The plastic one should deflect quite a bit more than the wooden one. Actually, you can even see that the plastic one is deflecting more under its own weight than the wooden one. The deflection under its own weight for a uniformly distributed load turns out to be proportional to the length to the fourth power instead of the length to the third power, and there would be a different numerical factor downstairs. But let's just see how it changes when we put a weight on the end. So I'm going to use a little binder clip to hold my weight on the end, and I'll put them side by side so they're easy to see. And notice that the undeflected height of each one is approximately the bottom of this first orange stripe. So it's about 90 centimeters off the ground, even though you can't see the ground. I'm going to put 200 grams on each one. Okay, so at the end, which is what we care about, the wooden one deflects, I would say, about 1 centimeter. The plastic one deflects, I would say about 5 or 6 centimeters. So it seems like the deflection of the plastic beam is about 5 or 6 times the deflection of the wooden beam under the same load. So I guess we could infer that probably the Young's modulus of the plastic might be 5 or 6 times smaller. There may also be some slight difference in the second moment of area for the two meter sticks. I think they might not have precisely identical cross sections. Let's see what happens if we double the weight that we put on each one. So I'll just load one of them at a time. So let's put 400 grams on the wooden meter stick. And now it does seem to deflect about twice as much. It seems to deflect about 2 centimeters instead of about 1 centimeter. We could do the same thing with the plastic one. Whoa, and I think it deflects more like 10 centimeters or so. Yeah, I'd say it deflects a little more than 10 centimeters, whereas originally it deflected probably a little more than 5 centimeters. Let's see, so if we do this, yeah, I think it deflects, I don't know, between 5 and 10 centimeters, a little more than 5. If we do this, I think it deflects, I don't know, 10 or 15 centimeters. Okay, so this deflection is supposed to be proportional to the weight we put on the end. It seems like that looks plausible. We have here two wooden meter sticks, one of them on edge like a joist and one of them on the flat like a plank, and they're both set to be cantilevers that are 1/2 meter, 50 centimeters long. And let's put a kilogram on the end of each one and see what happens. So here is a kilogram on the end of the one on the flat, and it deflects, I'd say, about 5 centimeters. And here's a kilogram on the end of the one that's on edge. Now, we said earlier this aspect ratio of these wooden meter sticks is a little more than 3, so when you square that, it's about 10. So I think this should deflect about 1/10 as much because of the bigger shape factor. And it seems like I would call it about 1/2 centimeter. This was about 5 centimeters, this was about 1/2 centimeter. So that's that I factor in the denominator of PL cubed over 3EI. So we make I about 10 times as big, then for the same load, the deflection is about 1/10 as big. We have here two wooden meter sticks, same material, same cross section, both on the flat like planks. This one is a 1/2 meter long cantilever. This is a 1 meter long cantilever. So the length of the cantilever is twice as long for this one as for this one. So if we put a concentrated load at the end, I think the deflection of this one should be 8 times as big as the deflection of this one. Let's put half a kilogram on the end of this one. It seems, well, okay, 11, 23. It seems to deflect about 12 centimeters. Let's put half a kilogram on the end of this one. It seems to deflect about 1.5 centimeters. That seems like pretty decent agreement with our expectation of 8 to 1. You absolutely don't need to know how to do this, but I think it's fun to know how to do this. I like calculus. So let's do another example. We can work out some of the classic beam deflection results. Here is a cantilever with uniform distributed load W. Okay, so W is the weight per unit length carried by the beam. So here's x equals 0 on the left side of the beam, x equals L on the right side of the beam, uniform load W. The wall on the left provides an upward force WL. It also provides a torque, which turns out to be WL squared over 2. So the shear diagram, which is the running sum, the cumulative sum of forces up minus down from the left end of the beam up to x, starts out at plus WL for the upward force exerted by the wall, and then it has a downward slope of W, so the slope is minus W, and then it reaches a value of 0 at the end. It should reach a value of 0 at the end because the free end of a beam should have both 0 force and 0 torque. Then we integrate that once to get the moment diagram. See, the load diagram is a constant, that's a 0th order curve. Therefore, the shear diagram, V, is a first order curve. Therefore, the moment diagram, M, is a second order curve. So we expect a quadratic curve, and we expect, see, so this maximum moment, WL squared over 2, you know it starts out at 0 on the right-hand side, and it's non-zero over here. It should be negative because a cantilever is frowning, not smiling. In other words, a cantilever is concave down, not concave up. The average value of this shear function is WL over 2. So you take WL over 2, which is the average height, times the width. That gives you the area under this triangle. So the area under this triangle is L times WL divided by 2. That's WL squared over 2, so that is the peak value of this moment function. We can write this in functional form. The moment as a function of x is minus W over 2 times x minus L, the quantity squared. As a check, we can take its derivative and make sure that that equals the shear function. So the derivative of this square comes down and annihilates this 2 in the denominator. So then we get minus W times x minus L. So then the minus sign outside can just swap the order of the two terms inside. We get WL minus x. And that indeed is what we see here. It's WL at x equals 0. It's a linear curve, and it is 0 at x equals L. Okay, now let's try integrating that twice. So you know, to get the deflected shape, capital Y, I use capital Y for the deflected beam shape. That's 1 over EI. This is Young's modulus. This is the second moment of area, which Onouye calls the area moment of inertia. And we're going to integrate twice with respect to x. Here we go. So for this first integral, if we say let u equal x minus L, then we have integral u squared du, and then this gives us du just equals dx. So the integral of that is u cubed over 3 plus some constant. So that is x minus L cubed over 3 plus some constant. We'll call this C1 because there'll be a second constant. So this is y of x is minus w over 2ei. We're going to integrate one more time, and we have 1/3 x minus L cubed plus a constant. Then we'll integrate this one more time. So I guess again we can say let u equal x minus L, du just equals dx, and we have the integral du of u cubed over 3 plus c1. So that is u to the 4th over 12. 3 times 4 is 12 plus c1u plus c2. Here's x minus L to the 4th over 12 plus c1 x minus L plus c2. Then we have two constants to determine. So let's do c1 first. So we know that y prime of 0 should equal 0 that's for the fixed end of a cantilever. The fixed end of a cantilever should have both 0 offset and 0 slope. This expression up here is y prime of x, or at least is proportional to it. So that says that 1/3 0 minus L cubed plus c1 should equal 0. Minus L cubed over 3 plus c1 equals 0. That gives me c1 equals L cubed over 3. Then we can just write that in here. Then we want to say that y of 0 equals 0, since the fixed end of a cantilever has 0 deflection. Also, any point which is supported on a beam has 0 offset. So that gives us 0 minus L to the 4th power over 12 plus L cubed over 3, 0 minus L plus C2 equals 0. So keeping C2 on this side moving, I can move this over to the right and it becomes positive, and I can move this over to the right and it becomes negative. So I have L to the 4th, 1/3 minus 1/12. 1/3 minus 1/12. This is 4/12 minus 1/12 is 3/12, which is a quarter. So we have C2 is L to the 4th over 4. So then we can just write that in here. Then let's plug in and see what we get for y equals L. In this case, we know just by inspection, that the end of the beam will be the part with the largest deflection. So we can just plug in x equals L and see what y is at x equals L, and that will, in this case, be our largest deflection. So y at x equals L is minus w over 2ei. So L minus L is 0. So that first term is 0. L minus L is 0. The second term is 0. And we get L to the 4th over 4. So this is minus w L to the 4th over 8ei. Okay, so that's the deflection at the far end of a uniformly loaded cantilever. Usually if you see this result written up in a table, it won't have the minus sign because the deflection is clearly going to be downward. So what's reported is the deflection. So you'll say, sometimes the deflection, delta, is the opposite of what we're calling y. Y is the shape that the beam traces out. So you say, well, how far does it go down? So that's just minus y. So then you say delta max, the maximum deflection, is w L to the 4th over 8ei. And I don't use these results the way Professor Farley does, so I looked at my notes and confirmed that this is indeed the accepted answer. That's good. We seem to have done it correctly. Let's try another example. How about a simply supported beam with uniform distributed load W? So W is the weight per unit length along the beam. The length of the beam is L. Here's x equals 0. Here's x equals L. We have a hinge support here, a roller support here, but really we just have a single vertical force at each end. And we know that each one of these must just equal WL over 2, since the load is symmetric and it has to add up to W times L. So then running sum, cumulative sum, up minus down from the left end of the beam up to x. So you start at 0. So at 0 you have plus WL over 2. Then we have a slope downward of W because that's our uniform weight per unit length. And then we get to the very end. Just before the very end we're at minus WL over 2, and then the support on the end takes us right back up to 0. Well, this is my favorite example because this graph looks exactly like the upward velocity as a function of time for a ball thrown straight up in the air. So you know the integral of this. So if this were the velocity in the y direction versus time, then you would integrate that and you would get this parabolic shape for the altitude versus time. So we can write a functional expression for this curve. Turns out to be, I just wrote down this curve and integrated it because I wasn't smart enough to write down this parabolic form directly from my head. So I got W over 2 as a coefficient up front, and then Lx minus x squared. And it's always nice to check. Derivatives are a lot easier than integrals, so it's nice to check. So let's check by taking the derivative. So the W over 2 is just a constant. So L times x, its derivative is just L, minus x squared, so its derivative is minus 2x. So there's W over L, L minus 2x, and we can multiply out. You get WL over 2 minus WX, and that, sure enough, is a v of x function. So let's try finding the shape of this beam. All we really want is the maximum deflection. The maximum deflection will happen at mid-span. I think you can tell that by symmetry. You know that this shape will bend into a nice symmetric smiley face. So the maximum deflection will be at mid-span. So we really just want to figure out what is y at L over 2. But before we can do that, we have to find a functional form for y versus x. This, again, you absolutely, positively do not need to know how to do this, but I think it's kind of fun. So y of x equals, so what's our coefficient? Our coefficient is w over 2. So this is w over 2ei integral dx integral Lx minus x squared dx. So there's m of x except for this factor, and that factor wound up outside, w over 2. I think that's good. Let's do this first integral. So the first integral, this x gives us Lx squared over 2. Then this x squared gives us x cubed over 3. And then there is a constant of integration. Then we're going to integrate one more time. So this x squared over 2, this is x cubed over 6. 3 times 2 is 6. This is x to the 4th over 4, but 4 times 3 is 12. And then this is c1x, and then there's another c2. Then we need to determine the constants. To determine the constants, y of 0 equals 0 and y of L equals 0. So the first one is easy. It just tells us that C2 equals 0. The second one is a little bit harder. So this says L cubed over 6 minus L 4th over 12 plus C1L equals 0. So we have C2 equals 0, C1 equals minus L cubed over 12. So this is 0, and this is minus L cubed over 12. Now we just have to evaluate y at L over 2, and that will turn out to be our maximum deflection, because by symmetry we know that this is going to be farthest away from 0 at mid-span. So let's just plug in x equals L over 2 and see what we get. Plugging in x equals L over 2, so we have y at L over 2. We have this w over 2ei out front, which works out to be 5w L to the 4th over 384 ei. Well, with a minus sign, actually. So that's y at L over 2 mid-span. which is the largest deflection. So that gives us the largest deflection is 5w L to the fourth over 384 EI. That's a really weird looking result, and you might wonder where on earth it comes from, and now you know where it comes from. It's sort of the fun thing about doing a little bit of calculus. You can see where these crazy things come from. By the way, one other classic result is if you had a simply supported beam with a single concentrated load at midspan. So you just had some single load P at midspan, no uniform load, just a single load P at midspan, then the result you would get would be the maximum deflection is P L cubed over 48 EI. If you can draw load and shear and moment diagrams and then do the calculus to prove this, and again, since it is right in the middle, the beam is smiling, so all you have to do after you integrate twice is plug in x equals L over 2, and remember you'll get a minus sign because y of x will go downward, but you want to know the maximum deflection. So by convention, delta max is minus y at whatever value maximizes the deviation of y from 0. So if you can work this out and send it to me, that's worth extra credit. Don't do it as a form of self-punishment. Do it only if you find calculus to be as much fun as I do. So we've been using the fact that one way to represent curvature is 1 over r, the reciprocal of the radius of curvature, and that in calculus that is approximately equal to the second derivative of the function y of x. In other words, positive second derivative is concave up, positive curvature. Negative second derivative is concave down, negative curvature. So we used this relationship between the second derivative and the reciprocal of the radius of curvature to write the second derivative of the deflected beam shape as the bending moment divided by Young's modulus divided by the second moment of area. And then we used that. If you liked calculus enough to watch the last example, you saw that we used that to work out this obscure looking result, which you'll see in many places, but how to get it is a bit obscure. 5WL fourth over 384 EI for the maximum deflection, which is midspan of a simply supported beam with uniform load W, and so on. So then back to this Onouye Kane figure. If you have a distributed load, W, that is a downward load, and since this shear curve V is the cumulative sum, the running sum of all forces up minus down acting on the beam from 0 up to x, then you add up not W but minus W, since W is downward, we want up minus down to get V. So if you have some function W representing a distributed load, then the shear function V is the integral of minus W. So that's how this thing being positive gets you a negative slope here. Then the moment curve is the integral of the shear curve. And again, this is one of my favorite examples because this looks like the velocity vertically versus time, and this looks like the position vertically versus time of a ball thrown straight upward. Then you can divide by EI and integrate one more time, and you get dy by dx, which is the slope of the beam. And then you can integrate that one more time, and you get y. I use capital Y for this rather than lowercase y because we've already been using lowercase y for the height above the neutral surface. So he writes little y, I prefer to write big Y. So this is the deflected shape of the beam under load. Okay, so now we've worked a few examples and we can see how this makes sense. And I guess then you can see the point of drawing these diagrams. Drawing these diagrams helps us to figure out, well, how much does the beam change shape when somebody steps on it, or when we put a bunch of furniture on top of it, or when somehow it carries a load. And then we can also ask, what are the internal forces, the internal stresses that the little fibers running along the axis of the beam that we imagine are there must bear, and are they excessive? Again, the most common deflection results can be found in tables, so you basically just look these things up when you need them. And we worked out this first one, 5W L to the fourth over 384 EI, and I left this one, PL cubed over 48 EI, as an extra credit problem if you're feeling really ambitious about your calculus skills. So basically either you remember them or you look them up, but calculating them is just something you might do for fun. So maximum deflection is one of several beam design criteria. So this maximum deflection comes from integrating this moment over EI twice with respect to x, and then plugging in the value of x where the deflection is largest. Maybe the more important point is that deflection is proportional to the load. So the more weight you put on the beam, the deflection increases in proportion to that. So if you take the same load pattern and you just double the weight everywhere, you'll double the deflection. If you use a stiffer material, you get less deflection. You can see this Young's modulus in the denominator. And if you use a cross section with larger second moment of area, also known as area moment of inertia, you'll get less deflection. You see this second moment of area I in the denominator. And in general, you have this factor EI in the denominator. So the stiffness of a beam is proportional to EI. So there's a part that comes from the material, the Young's modulus, and there's a part that comes from the cross-section shape, the second moment of area, also known as area moment of inertia. And then one thing to notice, if you have a uniformly loaded beam, the maximum deflection goes like the length to the fourth power. Usually if you have a point load, a concentrated load, the maximum deflection goes like the length to the third power. For a uniform load, the maximum deflection goes like the fourth power of the length. And this is because, you know, if you have a point-like distribution, then the shear diagram is 0th order, so then the moment is first order. You integrate twice, you get a third order curve. That's if you have point loads, concentrated loads. If you have a uniform load, then the shear diagram is first order, so the moment diagram is second order. You integrate twice, you get a fourth order curve. So with a uniform load, you get a maximum deflection proportional to the length to the fourth power, the span of the beam to the fourth power. So notice that if you stick a column in the middle of a long uniformly loaded beam, you reduce the maximum deflection by a factor of 16. 2 to the fourth power is 16. So it makes a pretty big difference if somehow you cut a span in half with a support in the middle. Alternatively, if you want to span a large open space without any kind of intermediate column or bearing wall, you generally need to use beams that have a large stiffness, so usually a large area moment of inertia, this factor I. So that's why if you look around a basement, then if you have very long spans, then you might see floor joists that have a cross-section that looks something like this. And if you have relatively short spans, you might see floor joists that have a cross-section that looks like this. So this is much stiffer than this is. And so for spanning a long distance, generally you need a larger second moment of area. This diagram indicates that for a simply supported beam, the fibers farthest down below the neutral surface are the ones that are most in tension, and the fibers farthest above the neutral surface are the ones that are most in compression. And then right along the neutral surface you have neither tension nor compression. And we have that spelled out in math over here, that the stress is the bending moment times the distance above the neutral surface divided by the second moment of area. And so if you want to know where is the axial stress, also known as the normal stress, largest, so which fibers of the beam are being pulled the most or squished the most, you look where the bending moment is biggest, and then you go to the fibers, the material that is farthest away from the neutral surface, and that's generally where you find the largest axial or normal stress in the beam. So that's one reason it's important to know what is the largest bending moment, what is the largest internal torque. So what's the peak, either the positive peak or the negative peak, what's the largest absolute value of this M curve. And then there's this geometrical quantity, which is the second moment of area divided by the largest deviation from the neutral surface. Usually this largest deviation is just half the total height of the beam. There's the second moment of area, and then divided by half the total height of the beam is this thing called the section modulus. Anyway, so the fibers that are most stressed in that along the axis of the beam are where this product of the bending moment and the distance, either above or below the neutral surface, is largest in magnitude. If you try bending a deck of cards, you'll see that neighboring cards tend to try to slip past one another in this way. That is a shear phenomenon. If you imagine that all of the cards are initially glued together and then you bend the deck of cards like this, or like this, then since the cards on the top of the deck are bent to a different radius of curvature from the cards on the bottom of the deck, there will be this slipping past one another shearing phenomenon. And then you can imagine that in some places that shearing would cause the glue between adjacent cards to fail if they're all glued together. So let's try studying this phenomenon of shearing stresses within a beam whose cross-section is rectangular. So here's a beam, and we drew it with a rectangular cross-section. So the width of the cross-section is b, and the height of the cross-section is h. That would give us our familiar bh cubed over 12 for the second moment of area I. And then here's L along the axis of the beam. So earlier we worked out this really useful result that the axial stress equals my over I. So remember, stress is force per unit area. So this m was the bending moment. So that's this m diagram we often draw. And let's imagine that this beam is a simply supported beam with a uniform load on the top. So it's going to bend into a smile. So then its m versus x curve would look like this nice parabolic shape. Notice that the slope of the M curve is largest at the ends. And actually remember, the slope of the M curve is the shear curve V. Professor Farley has a really colorful way to illustrate what's happening here. He says, suppose that the beam is composed of all of us lying down with our heads along the beam. So he draws all of our smiling faces at different places in the beam. He says, where do you want to be in this beam full of smiling faces? You probably want to be where the stresses are smallest. I won't try to imitate his performance. You have to see it for yourself sometime. Maybe we can get a video clip of it sometime to splice it in here. Anyway, let's try to analyze the forces acting on some little chunk of the beam right here. And I'm only going to worry about the two-dimensional slice. I'll just pretend I'm looking at the plane and not worry about the third dimension. I mean, I guess in principle what I'm doing is I'm really adding up over the width B of the beam. So the bending moment is this big over here. Let's call this A. Let's call this B. No, I won't call it B. We've already used the letter B. Let's call this alpha, and let's call this beta. I just hesitate to use the letter B because B is already used here. So here's alpha and here's beta. So we can see the moment function is a little bit bigger at alpha than it is at beta. And the fibers of this beam, well, here's the neutral surface. So above the neutral surface we are in compression, and below the neutral surface we are in tension. But let's just look at this piece up above the neutral surface for now. And you know that these forces per unit area are bigger in proportion to how far up I am above the neutral surface or how far down below. So these little arrows will get shorter as we get closer and closer to the neutral surface. Also notice that all of the arrows are smaller on the right side than they are on the left side because they have to add up to a smaller bending moment on the right side than on the left side. we know that this little chunk of material must be in equilibrium. It's not going anywhere, so all the forces on it must balance. And the way we've drawn this here, all the forces on the left add up to a bigger magnitude pointing to the right than all of the forces here on the right side pointing to the left. Our little chunk of material ends at the very top surface of the beam, so there's no force in this direction along the beam axis at the very top end of the beam because there's no material there. So to put this into equilibrium, there must be another force pointing this way, so that all of the stuff pointing to the left balances all of the stuff pointing to the right. And you see, for each one of these arrows pointing to the right on the left side of this chunk, there's another arrow pointing to the left on the right side of this chunk, but these arrows are all longer than these arrows because the moment function is bigger here than it is here. Each one of these little arrows is proportional to this moment function times the height above the neutral surface. So if we didn't have this blue arrow pointing to the left, then this little chunk of beam would be out of equilibrium because we would have a net force pointing to the right. So that would not make sense. So to make all the forces add up to zero, there must be a force pointing to the left exerted by the material down below, just below this little hypothetical piece of the beam that we've, in our mind's eye, partitioned off. So that is the shear force, or shear stress. If you want to make it a force per unit area, it's a stress corresponding to the forces between parallel fibers of the beam. If we again imagine the beam to be a whole bunch of little like fibers of a piece of wood running parallel. Even though most materials don't take that form, I think it's still a useful metaphor. So there has to be some shear force or shear stress, like the glue between adjacent cards in my deck of cards, exerting the force corresponding to this little blue arrow below this hypothetical chunk of beam. So I can start at the very top and I can go down to some height y above the neutral surface. So here's the height y above the neutral surface. And this little blue arrow turns out to be the shear stress, which usually we write as a little f for stress. So we have big F for force and we have little f for stress, and then we put a subscript v indicating that it is shear, a shear stress. So it's the force per unit area, but instead of trying to pull the fibers to elongate them or pushing them to squish them, instead it's like trying to make the fibers slide past one another. So if I call this distance delta x, since we have x running along the length of the beam, then this shear stress is a force per unit area. And what is the relevant area? The relevant area is delta x times b, the width of the beam. So let's call this x, and this is going to be x plus delta x. So these forces in magenta acting to the right are m of x times y over I, and then we have delta A. Delta A is going to be some little chunk of cross-section here. We're adding up over that cross-section. Then we have the forces to the left. So we have minus m of x plus delta x, y over I, delta A. Then we have this shear force to the left, which is minus fv b delta x. And that all has to add up to 0 to keep this little chunk of beam in equilibrium. Also, to do this properly, we have to add these things up over all little patches of area, delta A. So we'll do that also. We'll add up over all the little patches. So I guess we can say minus fv b delta x. And I have a feeling that my minus sign is going to turn out to be because I should have picked the other side of the beam. We can just compare when we're done the result with what I wrote in my notes earlier. So then we're going to sum over all little chunks delta A, and we have m of x plus delta x minus m of x times y over I delta A. This expression is just dm by dx times delta x from calculus. And dm by dx actually is v of x. But I'll leave it in the form dm by dx for the moment. So this is dm by dx times delta x, and then we're going to divide by I, and then we're adding up over all little patches of area, y delta A. And this somehow equals minus our shear stress times the width of the beam times delta x. Well, we can cancel the delta x from both sides. Also, this delta A up here, well, we're going to add things up over the whole cross-section. The only variable we're changing here is y, the distance up from the neutral surface. So everything is constant across this width of the beam. So we can say delta A is actually b delta y. So then we have, this minus sign irritates me. I must have made a mistake. This is the danger of working extemporaneously instead of from notes. Minus fvb equals, well, dm by dx really equals v of x, right? So dm by dx, we also notice that dm by dx equals v of x. So the derivative of the moment function is the shear function. So I'm just going to replace this with v of x. So we have v of x over I, and then we're going to sum up over all little chunks of area, y, and then our delta A is actually b times delta y. Then you notice we can cancel this factor b from both sides. So we have minus this shear stress is v over I, and this is really an integral rather than a sum, and it's the integral y dy. And we're going from the very top of the beam down to y. So we're going from h over 2 for a rectangular beam down to some value y. So when we integrate this, we'll get y squared over 2 integrated, evaluated from y equals y up to y equals h over 2. So that equals h over 2 squared minus y squared. So I wrote this in, I factored out a factor of h squared over 4 here. So I could make this 1 minus something proportional to y squared. And then we could plug in for a rectangular beam cross section I equals bh cubed over 12. And in fact, in this case, we want to use the area equals bh. So this is actually area h squared over 12 so that we can write it in terms of the area. So this gives us b h squared over 8, and then this 1 over I, this gives us 12 over a h squared. And then we have this factor in parentheses, 1 minus 2y over h, the quantity squared. And we can cancel the h squared. Then this 12/8 becomes 3/2. That was a pretty confusing mess of math, but what is this actually telling you? It's telling you that if you have a rectangular beam cross section, and if we have a simply supported beam with uniform load, which is a nice, somewhat typical case, then the shear stress, the stresses trying to pull those parallel playing cards past one another. The shear stress, the forces internally trying to slide those internal playing cards in the deck of cards parallel to one another, are largest where this shear function v is largest. So maybe now it makes more sense that this derivative of the moment function is called the shear function v, because the shear stresses in the beam are proportional to v. And then it seems like it makes sense that since stress is force per unit area, that and v is a force, right? So this v diagram is measured in units of force. So if you want to turn it into a stress, you want force per unit area. So if you take this v function and divide it by a, that kind of makes sense. It's force per unit area. And then you say, what's the biggest possible value of this function in this rectangular beam? And it seems like this thing in parentheses is biggest when y equals 0. That means what's biggest when we're at the neutral surface. And what is the biggest value? The biggest value is 3/2 v over a, 1.5 times v over a. And so this is the shear stress in a beam of rectangular cross section. So it's largest where this shear function v has the biggest magnitude. It's proportional to this shear function divided by the area of the cross section. And the largest value is actually 3/2 v over a for a rectangular cross section. And it's largest at the neutral surface. And it's largest at the simply supported ends of the beam. So there's a graph in Onouye that looks something like this. And here's y equals 0. And all of this math I just wrote on the board is basically the outcome of my looking at that drawing in Onouye and trying to understand why it has the shape that it has. And I then asked Prof Farley, and he gave a nice intuitive explanation, and then I turned his nice intuitive explanation into all of this math. You would probably prefer his intuitive explanation. So we're going to notice on the next slide that for most load and support conditions, the bending moment varies as a function of x, the length along the beam, and the bending stress, in other words, the axial stress in the fibers is proportional to this bending moment. We know that. It's the bending moment times the height above the neutral axis divided by the second moment of area. The shear stress exerted between parallel fibers along the bottom edge of the red rectangle, well in this case I drew it as an orange rectangle, must make up the difference between the left and the right total bending forces. So this has to make up the difference between all this and all this. The left and right total bending forces depend on how much area we add up in drawing the orange rectangle. Okay, you can kind of see that. So how far down we go. In fact, you see, actually this kind of makes it clear. So at the very top, you're only adding up a little bit of these left and right arrows. So this blue arrow, if you were going to do this much higher up, like if you were going to do this much closer to the top surface of the beam, I'll just do it symmetrically on the opposite side. Then, okay, so in this case, the bending moment is bigger over here and it's smaller over here because it's the symmetric situation. So you can see that I don't have to add up as many arrows if I take a smaller bite here. If I take a smaller bite here instead of this bite, then I only have to add up a small number of arrows. And so this offsetting arrow can be much smaller. But as I increase the size of the bite that I take here, then I would have to add up more and more and more little arrows. So then this offsetting shear force or shear stress has to be bigger. Then by the time I go on the opposite side of the neutral surface, now I'm starting to add bending forces, axial forces in the opposite direction because I go from being in compression to being in tension. So then you get these little magenta arrows in the opposite direction. And so then they start to subtract from what we added up above. So the total that you get going from the top surface of the beam and stopping at some depth as you take out your imaginary chunk of the beam, that total adds up to the biggest total when we are right at the neutral surface. So these shear stresses are actually biggest at the neutral surface, and how big they are is proportional to this shear function v. And this shear function V is telling you how does the bending moment change from one side of this chunk to the other. And you know all of these little axial stresses are proportional to this bending moment times how high we are up above the neutral surface. So the total reaches a maximum at the neutral surface, and then it decreases because the direction of the bending stress reverses. In other words, it goes from being compression to being tension at the neutral surface. Here's this Onouye figure, and then here's my annotated two little chunks. So here's taking a little small bite, and here's taking a much bigger bite. And if you take a small bite, then you only have to offset a relatively small difference in the sum of these little arrows up here. But the farther down I go, the more of these little arrows I have to add up. So here again is Onouye's diagram, which I annotated a little bit, trying to make the same point I was making with this chunk and this chunk. And then here's Onouye's nice diagram showing this parabolic shape. Though I think it's kind of fun to point out that his parabola doesn't look like a parabola, even though the math says it really is a parabola. In any case, you can see that the way he drew it, the function is largest at the neutral surface, which is correct, but it actually doesn't have a point like this. It's actually a nice parabola. This, by the way, is way beyond the scope of this course. I just worked it out because I thought it was fun to work it out because I saw it in the book and I wanted to understand it. I have a mathy description written up in the equation sheet, and I think we should find a way to splice in here Professor Farley's really colorful description of the same phenomenon, using his diagram of a beam with a whole bunch of people's heads side by side and figuring out where they want to be in the beam. That was all extremely abstract. Let's go back to something much more concrete, like drawing shear and moment diagrams. I'm going to pretend these units are metric because I really dislike US customary units. So we have to solve for the vertical support forces at this position that Onouye calls B, and at this other position that let's just call R for the right hand side. So this will be By, and this will be Ry, and I'll put the little slash through them the way he does. And to work out the support forces, we initially replace the distributed loads with equivalent, in other words equivalent for the purpose of static equilibrium, equivalent concentrated loads. This is 2 kilonewtons per meter times 10 meters equals 20 kilonewtons, and then this is 10 kilonewtons. So this distance is 10 meters, and then this distance is 15 meters, and this distance is 5 meters. Let's solve for By by pivoting about R. So we'll do 0 is the sum counterclockwise about R of the torques, or we could say moments. So this is our pivot. So we can do 20 kilonewtons times 5 meters plus 10 kilonewtons times 30 meters minus By times 20 meters. That gives us By equals 1 over 20 meters. This is 20 times 5 is 100 kilonewton meters plus 30 times 10 is 300. So 100 plus 300 is 400. 400 kilonewton meters divided by 20 meters is 20 kilonewtons. So it seems like this is 20 kilonewtons. And then we know that By plus Ry equals 30 kilonewtons. So all the downs add up to 30 and all the ups add up to By plus Ry. So that gives us Ry is 30 minus By, which must be 10. So this is 10 kilonewtons. Okay, so this is 20 and this is 10. So then this is our load diagram. And then we can erase and make room to draw the V and M diagram. Okay, now we can draw our shear diagram. Plus 0 minus. So we want the running sum up minus down, starting from the left. So we go down to minus 10 and we stay there for a while. Then we have plus 20. So plus 20 brings us from minus 10 up to plus 10. And we stay there for a while. Then we have a slope of minus 2, which will bring us to minus 10. See, just before the end we should be at minus 10, and this 10 should bring us back to 0. So this should be minus 10 over here. So this is then minus 10 kilonewtons. That's a pretty funny shape. Okay, then we want to turn this into an M curve. It's going to be 0 at both ends because it's an end. It's the type of end that cannot sustain a non-zero moment. So this is a 0 order curve. So we have a first order curve. So we're going to have a slope downward. Slope is minus 10 kilonewtons. Then we have that same slope upward for that same 10 meter length. So we're going to come back to 0 here. And now we see we're starting from 0 and we have that baseball thrown up in the air shape. So we know this is going to be a parabola. Although I didn't quite do this right because it should be a parabola whose initial slope is the same as this slope, since this slope starts out up here. So I can make it more graphically accurate like that. So here is the shape we fill in. And then the question is, what is this maximum value? So this value down here, this is minus 10 kilonewtons times 10 meters. So that's 100. Minus 100 kilonewton meters. And what is this? Well, I guess we can start from the end and go back. So this distance is 5 meters. So what's the area of this triangle? You see the change from here to here is just the area of this triangle. The area of this triangle is 5 meters times 10 kilonewtons divided by 2. So that's 5 times 5 is 25 plus 25 kilonewton meters. So you see the area of that triangle is just the base times the height divided by 2. Now, it turns out that this is a problem that Onouye has solved for us. He has this nice little drawing. Okay, our reaction forces agree with him, although we pretended the units were metric. And then his diagrams, so he has shear diagram that looks just like ours. Minus 10 to plus 10, back to minus 10. 10. And then his maximum negative moment is minus 100, which agrees with us. And his maximum positive moment is plus 25, which agrees with us. So I think we're getting pretty good at this. Okay, so here's another Onouye shear and moment diagram problem. So let's start out by solving for the support forces. So we have AY over here, we have CY over here, and 2 kilonewtons per meter times 10 meters, I'm pretending the units are metric units, is 20 kilonewtons. We'll put that, since it's flat, we'll put it at the centroid. So there is 20 kilonewtons, and this distance is 5 meters, and this distance is 15 meters. So let's pivot about A to find CY. So we'll pivot here. So 0 is the sum about A of the torques, also known as moments. So we have CY times 20 meters minus 20 kilonewtons times 5 meters equals 0. That gives us CY equals 5 kilonewtons, because we have 20 times 5 divided by 20, which is 5. So this equals 5 kilonewtons, and then they must add up to 20, so this is 15 kilonewtons. You see, our sum of forces in X equation would give us AY plus CY minus 20 kilonewtons equals 0. So the two support forces have to add up to 20. We know one of them is 5, so the other one must be 15. This also makes sense because this support is 3 times as far away as this one. So to balance about this force, this will be 3 times larger with 1/3 the lever arm. This will be 1/3 as big with 3 times the lever arm. So that makes sense, because it's a 3-to-1 ratio, and the one that's farther away is smaller. Okay, so now we can erase these things and indicate that this is 15 kilonewtons and this is 5 kilonewtons. Now we can erase and make room for the V and M diagram. For the shear diagram V, we want the running sum up minus down of the vertical forces on the beam. So we start out with this plus 15. So here is an immediate jump up to plus 15 kilonewtons. Then we have a downward slope of 2, and where are we going to wind up? Well, somehow when we get to this end, just before this end, we'll be at minus 5, and then this 5 will bring us up to 0. And then this must be flat until halfway across the beam, and then this must be a constant slope of minus 2. So I think that's what our shear diagram will look like. This is actually a straight vertical. Then the moment diagram, this again is kind of like our tossed baseball up vertically. So I think, and it should reach, where does this reach 0? 15 minus 2 times 7.5 is 0. So this crosses 0 at 7.5 meters, right? Because 15 minus 2 times 7.5 is 0. So I think we go like this, parabolically up to 7.5, and then we continue on the downward part of that parabola until we reach 10. And then, now we just slope down with a constant slope. So this is a slope, is minus 5 kilonewtons. So this is our shape. So it's kind of 3/4 of a parabola, or I don't know, maybe 60% of a parabola, and then there's a downward slope. And what is this M max equals? This must be, right, see, this is 7.5. What's the area of this triangle? The area of this triangle is 1/2 times the base times the height of the triangle. So that is 1/2 times 15 kilonewtons times 7.5 meter, which is, believe it or not, 56.25. So I think that's the answer. Let's see. Well, we have Onouye's drawing. He gets a support force of 15 on the left and 5 on the right. That makes sense. And then his drawings have that same shape. You go up to plus 15, and then you slope down to minus 5. And then his peak value is also 56.25. It's just that he uses imperial units, and I preferred to pretend that this was specified in metric units. Neat. We did it. We're getting good at this. Okay, the next few slides contain beam design examples of the sort you might see in a structures course. Example, using metric units. A cantilever beam has a span of 3 meters with a single concentrated load of 100 kilograms at its unsupported end. If the beam is made of timber having allowable bending stress 1.1 times 10 to the 7th newtons per square meter, which by the way was, that was originally 1,600 pounds per square inch in US customary units, what minimum section modulus is required? Then what is the smallest 2x dimensional lumber, width of 1.5 inches, which is 0.038 meters, that's 3.8 centimeters, whose cross section satisfies this strength criterion? Well, that could be interesting. Oh, would this beam also satisfy a maximum deflection L over 240 stiffness criterion? If not, what standard 2x cross section is needed instead? This could be interesting. We can use PL cubed over 3EI for a cantilever with concentrated load at the end for the deflection, and we can use Young's modulus 1.110 to the 10th newtons per square meter for southern pine. Okay, let's go. So a cantilever with a span of 3 meters. So that looks like this. Then we have the shear diagram looks like this. 100 kilograms means a force M equals 100 kilograms. So that means P, which is mg, is 980 newtons. So this is 980 newtons. Then we have the M diagram, and it has to come back, it's negative, and it has to come back to 0 at the end. So it must look like this. So first order curve, because this is a 0th order curve, and we have 980 newtons times 3 meters is, I'm going to say this is approximately 1,000 newtons. This is 3 kilonewton meters. So we're going to say 1 kilonewton because that's a lot simpler. Then this is minus 3 kilonewton meters. Okay, so that tells us M max in absolute value is 3 kilonewton meters. And we have an earlier result for axial stress. F, axial, I think it's often B for bending, is the bending moment moment times the height above the neutral surface divided by the second moment of area. And it turns out there's this thing called section modulus. This is pretty obscure. Section modulus, S, is the second moment of area divided by the maximum height above the neutral surface, which basically is just half the height of the beam if it's a rectangular beam or an otherwise symmetric beam. So this anyway is m over s, because this will be the maximum m and the maximum y, and this is the maximum y. That tells us the section modulus has to be bigger than or equal to the bending moment max divided by the allowable bending stress. So that gives us the minimum section modulus is the maximum absolute bending moment divided by the allowed bending stress, allowable. So that is 3 kilonewton meters divided by 1.1 times 10 to the 7th newtons per square meter, and that equals 2.73 times 10 to the minus 4 meters cubed. Now meters cubed is kind of crazy because we're talking about something that's the dimension of like a beam cross section. So that turns out to be 273 centimeters cubed, which is a little more convenient. So I think we need to find a 2-by whose section modulus is at least 273 cubic centimeters in order not to put too much axial strain on the fibers of the beam. Now, what's the smallest 2-by dimensional number which satisfies that? Well, for a rectangle, we have the second moment of area I is bh cubed over 12. So then the section modulus is I over ymax, which is bh cubed over 12 divided by h over 2, which is bh squared over 6. So we don't need these anymore. For a rectangular beam cross section, the section modulus is bh squared over 6. So that's this second moment of area divided by half the height. So we actually have a table, we can look this up, but we have b equals 3.8 centimeters, and we need s is bigger than 273 cubic centimeters. So that tells us we need h is bigger than, say we need the section modulus bigger than 273 cubic centimeters. We could just solve for the height we need, and that would give us about 21 centimeters, which is about 8.25 inches. So a 2x8 is 7.5 inches tall. So we would need a 2x10, which is 9.5 inches tall for our next size up of dimensional lumber. So a 2x8 would be not sufficient. So I guess we need a 2x10. And I have all these in a table in a moment. So over here, I have a table, and you see if we need 273 cubic centimeters, well, you see a 2x8 is too small. A 2x10 is easily big enough for that section modulus. So we have 230 cubic centimeters for 2x8. That's not big enough. 370 for 2x10 is big enough for this criterion. This is a strength criterion. There are going to be there's also going to be a stiffness criterion. Okay, I re-summarized that up here. So for the bending stress criterion, we need a section modulus bigger than 273 cubic centimeters, which implies we need a beam depth at least 21 centimeters, which is about 8.25 inches. So that implies we need 2x10 dimensional lumber. A 2x8 will not suffice. Then, okay, would this beam also satisfy a maximum deflection less than L over 240 stiffness criterion? Let's see. So we have maximum deflection, delta max equals, that's a capital delta, P L cubed over 3 EI. And we have I equals BH cubed over 12 for a rectangular beam cross section. And we're going to use Young's modulus equals 1.1 times 10 to the 10th newtons per square meter for southern pine timber. So we say delta max allowable is no more than L over 240, which is 3 meters over 240. So it's a little bit more than a centimeter. 300 centimeters over 240, 1.25 centimeters, about half an inch. Okay, so maximum allowable deflection for this 10-foot span is about half an inch. And will that work? So the concentrated load at the end was 1,000 newtons, 1 kilonewton. Actually, 980 newtons was the precise answer, but let's call it 1,000 newtons. And the L was 3 meters. And then we said B is 3.8 centimeters and H is 9.5 inches times 2.54 centimeters per inch equals, this is if we choose a 2x10 for dimensional lumber, that's 24.13 centimeters. So this would give us I equals BH cubed over 12 equals 4449 centimeters to the 4th power, which is 4.45 times 10 to the minus 5th meters to the 4th power. So you see meters are kind of an outrageous unit to use for the transverse dimensions of a beam. So if we plug in numbers, that's 0.0184 meters equals 1.84 centimeters. So that's not good enough because the criterion was it can't deflect more than 1.25 centimeters. This will deflect a little under 2 centimeters, 1.84 centimeters. Professor Farley tells us that normally the stiffness criterion is the most stringent, more stringent than the strength criterion. That bears out to be true in this case. So let's see what happens if instead we use a 2x12. So this was 2x10 dimensional lumber. So if we use a 2x12 dimensional lumber, then that means we have 11.5 inches times 2.54 centimeters per inch. So its depth is 29.2 centimeters. So we'll not do this. Instead, we'll plug in H is 29.2 centimeters for a 2x12. So that gives us 7.884 centimeters to the 4th power, which is 7.88 times 10 to the minus 5th meters to the 4th power. Always looks a bit odd in meters. So then we can recalculate this. So we we won't use this. We will instead use this updated version of the second moment of area. Okay, and we get 1.04 centimeters, which is just fine. I mean, it's actually 0.0104 meters, but I put it into centimeters. 1.04 centimeters. So that's kind of interesting. We increased the beam cross-section from a 2x10 to a 2x12. And that little increase of about 20% in height got us almost a factor of 2 in reduced deflection. Cool. Okay, it seems like for the strength criterion, a 2x10 dimensional lumber would have been sufficient. But then when we also evaluated the stiffness criterion, it turned out that wasn't good enough. We had to use a 2x12 dimensional lumber. And this was for a 3 meters, it's about 10-foot span with a 100-kilogram load in the middle. So here is the solution I previously wrote up. I think that looks just like the diagrams we drew earlier, although I think I might have drawn the cantilever mirrored here. So I made the free end at the left. I think on the board here just a moment ago I made the free end on the right. And okay, so I think I used 980 instead of 1,000, so I said 26.7 instead of 27.3 times 10 to the minus 5th meters cubed for the section modulus. Anyway, that's basically the same. And then we had an allowed deflection of 1¼ centimeters. And so this deflection criterion implies that we need a second moment of area of at least 6,420 centimeters to the fourth. And we can look at our table. 2x12s have 7,913. Okay, I just now worked out 7,884. Maybe 7,913 uses more precise values. So the 2x10 would have been 4,461. That's not good enough. 2x12 is 7,913, which is certainly good enough. And then for the section modulus, the bending stress criterion, we needed 273. So a 2x8 would not have been sufficient. That's 230. But a 2x10 is more than sufficient for the bending stress criterion, because that would be 370. So you see, normally they're just pre-calculated tables. I think I calculated this table though. Right, using, you see, 1½ inches by 3½, 5½, 7½, 9½, or 11½ inches. Okay, then in a moment we'll move on to a minor variation on this same problem. Here's another very similar problem, also from Onouye Kane. A cantilever beam has a span of 3 meters with a uniform distributed load of 33.3 kilograms per meter along its entire length. If we use timber with allowable bending stress 1.1 times 10 to the 7th newtons per square meter, what minimum section modulus is required? That's basically saying, like, how tall a 2x do you need? What beam cross-section do you need to satisfy this strength criterion? What is the smallest 2x dimensional lumber whose cross-section satisfies this strength criterion? Would this beam also satisfy a maximum deflection less than L/240 stiffness criterion? If not, what standard 2x cross-section is needed instead? Delta max is W L⁴/8EI for a cantilever with uniform load. Use Young's modulus 1.1 times 10 to the 10th newtons per square meter for southern pine. By the way, we are going through these examples not because you're going to come out of this course knowing how to do beam design. You have to take a real structures course to learn something like that. Rather, we're going through these examples to illustrate the point that having studied forces and torque and vectors and practiced these ideas and solved many problems with static equilibrium and solved many problems analyzing forces and torques leaves us with insight into real-world phenomena. An example of a very down-to-earth real-world phenomenon that we can now understand is what is the basic idea of the process that an architect or engineer goes through to figure out whether beams supporting the floor of your house are this tall or this tall or this tall. Or when you look at an I-beam, you understand now why it has that I shape. It's not for aesthetic reasons, it's for strength and stiffness reasons. We study these examples not because this course is intended to teach you these details, but rather that this course is using these real-world applications to illustrate the power of your understanding now of forces and torques and vectors and how they connect with real life. So let's draw a cantilever beam. So here's a wall, and here's a beam coming out from the wall, and we're going to call this the load diagram. And the load on this beam is uniform, and it's W equals 33.3 kilograms per meter times little g is 333 newtons per meter. Let's just call it G equals 10. The difference between 9.8 and 10 is only 2%. This length is 3 meters. And now we want to draw the shear diagram. So here's V, here's X. So there's no force at this free end. So we just start at 0 and we have a downward first order curve, and then we come back up to 0 at the very end. So this is slope equals 333 newtons per meter. And then you do that for 3 meters and we get 1 kilonewton at the end, minus 1. Slope is minus 333 newtons per meter. So multiply 333 by 3, you get 1,000. So that's minus 1 kilonewton at the bottom. By convention, we usually shade in this area to guide the eye. Now we want the moment curve. Okay, so this shear curve was basically what is the force that the left side of the beam exerts on the right side of the beam, or vice versa, if you cut the beam at coordinate x. And this is the torque. So a free end exerts no torque, so it will start at the left side at 0. And this is a first order curve. The integral of a first order curve is a second order curve. So this second order curve will be a parabola. It looks like this. So the maximum deviation from 0 of the shear here is 1 kilonewton in the negative direction. The maximum deviation from 0 of this torque or moment diagram is the area under this curve. curve. The area under this curve is, it's a triangle. So the area of a triangle is 1/2 times the base times the height. So this must be minus 1.5 kilonewton meters is the moment curve's maximum deviation from 0. Okay, then we know that the bending stress, FB, is my over I, which is just m over s. So this geometrical combination of the second moment of area divided by the largest excursion away from the neutral surface is clumped together into one factor s called the section modulus. So that gives us that the minimum section modulus is the bending moment divided by the allowable bending stress. So this is 1.5 kilonewton meters divided by 1.1 times 10 to the 7th newtons per square meter. And when we divide, so remember this is 1.5 10 to the 3, since the K is 10 to the 3. So that's 1.36 times 10 to the minus 4 meters cubed, but it's probably more useful to express it in centimeters cubed. So that's 136 centimeters cubed. So then we can figure out, looking back at our table of section modulus values for 2x lumber, it seems like a 2x6 is just a little bit too small a section modulus. So it seems like a 2x8 is what is called for, since 2x6, which would be 124 cubic centimeters, is too small. Okay, so for this strength criterion, the minimum section modulus that we can use is 136 cubic centimeters. And looking at the chart, 2x6 would be too small, a 2x8 is fine. There's probably a solution to this in Onouye that uses US customary units. I converted it to metric units on purpose to avoid using US customary units. Before we go on, let's see if we have an answer from Onouye to compare with. So it looks like his diagrams look just like ours. Oh, I see. In this case, actually I think these are my diagrams. And here I wrote this in generalities instead of with numbers. So WL squared over 2 would be 333 times 9 over 2, which indeed is 1500 Newton meters. That's good. So my pre-calculated answer was 1.33 times 10 to the minus 4. So that's pretty close to the 1.36 I got here. I probably used 9.8 instead of 10 when I calculated this before. Okay, then would this beam also satisfy a maximum deflection less than L over 240? So let's figure out. So delta max allowed is L over 240. So 3 meters over 240 is 1.25 centimeters. Then we can plug in delta max equals W L to the 4th over 8 EI. Oh, I don't know if we have I here. So we're going to try this for the 2x8. Well, no, you know what we'll do? Let's just solve for I. So the minimum value of the second moment of area that we need to satisfy this problem is W L to the 4th over 8 E delta max, because I went over to the left, delta max came down here, and with delta max is 1.25 centimeters, so we can plug in numbers. Okay, so I showed you how I plugged in numbers here. W was 333 newtons per meter, L was 3 meters, we're raising that to the 4th power, there's 8. The Young's modulus was 1.1 times 10 to the 10th newtons per square meter, and then the maximum allowed deflection was 1.25 times 10 to the minus 2 meters. So remember it was centimeters. So 1.25 centimeters is 1.25 times 10 to the minus 2 meters. So that gave me 2.452 times 10 to the minus 5th meters to the 4th power, which is kind of messy to write. So then I rewrote it in centimeters to the 4th power, 2452 centimeters to the 4th power. Then we can look back at our table of second moment of area for 2x's and 245. So it turns out a 2x8 is not sufficient. So 2x8 would be 2195 for this I value, second moment of area, also known as area moment of inertia. It seems like we need a 2x10. So in this case, we have determined that we need 2x10 dimensional lumber. So once again, we see results confirming Professor Farley's rule of thumb that the stiffness criterion is usually the most stringent. In other words, if you design for the stiffness criterion, usually that will turn out to satisfy the strength criteria. Whereas if you go the other way around, then the stiffness criterion will require something more stringent than what the strength criteria required in most cases. So he tells me. So it seems like we decided that a 2x8 would be okay here, but this implies 2x10 needed. Okay, so for the deflection requirement, it turns out this load on this span implied a 2x10. And notice that it is a lot easier if you could just go to a table and look up the values instead of having to do a whole bunch of math. Here is an actual homework problem from Professor Farley's structures course. Size, a wood joist for a row house floor, which spans 12 feet. We have L equals 12 feet. Joists are spaced at 16 inches on center. Okay, so joist spacing equals 16 inches. So I'm going to call this JS. And he is telling us that the live load is 60 pounds per square foot. Whoa. And the dead load is 30 pounds per square foot. So the dead load plus the live load is 90 pounds per square foot. So we have a floor like this, and there is a load of 90 pounds per square foot on that area. So that's the force per unit area. And we have this spacing, I'm going to call it JS for the joist spacing. We have force per unit area times the joist spacing, and that's going to give us force per unit length along each joist. This is where that Onouye chapter 4 on load tracing comes in. So the tributary area for one joist actually goes from halfway to this one to halfway to this one. So that distance, that tributary area, is one joist spacing wide. So you take really the distance from halfway between these two to halfway between these two, and that tells you what this one has to cover per unit length. Then we have this irritating issue. We're using both feet and inches in the same problem. This is a difficulty with US customary units. So let's stick with feet for the moment. So we have 90 pounds per square foot. That's the force per unit area. A pound is a unit of force. And then we have 16 inches between joists. So we multiply these together, we'll get force per unit length along one joist, which is what we want, but we have to do a unit conversion. So let's say we have 1 foot per 12 inches. Now we're going to get pounds per foot along the length of the beam. So that is 120 pounds per foot. So that's W, right? That's the load per unit length along the beam. So we have W equals 120 pounds per foot. By the way, Richard Farley sometimes comes into my class and solves the homework problems with the students. So it seems only fair that I should solve some of his homework problems too. Probably in Professor Farley's course you can use a table with common results derived already, but I don't have a pre-computed table. So here's a simply supported beam with uniform distributed load W. So that means that we have, this is WL over 2. That's a reaction force, WL over 2. This length is L. Well, this is the load diagram. Then we need to draw a shear diagram. This shear diagram will start off at WL over 2. It will have a slope of minus W, and then it'll have a value of minus WL over 2 on this end. And then we can draw the moment diagram. And since this looks like the velocity curve of a ball thrown straight upward, this will look like the position curve of a ball thrown straight upward. And all we need to do is figure out the maximum value here. And that maximum value will equal the area under this triangle. So for a triangle, area is 1/2 base height, so that's 1/2 L over 2. This is L over 2, and then that height is WL over 2. So this must be WL squared over 8. WL squared over 8. Using this, Mmax is WL squared over 8. I plug in 1/8 of W is 120 pounds per foot. That's the force per unit length along the beam. A joist is a kind of beam. And then the length of the beam is 12 feet. To take that L and square it, and this gives us, working out the units, we get 2,160 foot-pounds. A foot-pound is a unit of torque in US customary units. A foot-pound is also a unit of work or energy in US customary units, it turns out. Just like the Newton meter is a measure both of torque and of energy in SI units, the foot-pound is a unit both of torque and of energy in US customary units. Then, looking at Professor Farley's inputs, I'm going to interpret this top value of lowercase f to mean the allowable bending stress is 1,300 pounds per square inch, which is comparable to the value we used in metric units in the previous example. And then I can't read the exponent in his Young's modulus, but it seems like it should be 1.7 times 10 to the 6th pounds per square inch. That is a sensible value for southern pine, for example. And I'm not sure what his other value of lowercase f is. I wonder if it is an allowable shear stress. I'm not sure. So the first thing to check is the maximum deflection. I think it should be L over 360. We'll have to ask him also whether the building code says L over 360 or L over 240. And then meanwhile, this is a simply supported beam with uniform distributed load. So this is 5 over 384 WL to the 4th over EI. We worked that out with calculus. So we know the maximum deflection. Again, we have to ask Professor Farley about this. I think whether it's L over 360 or L over 240 might depend on whether or not it's supporting a plaster ceiling. So we know our delta max allowable value. So then we can just move this delta max down here and move I over here so we can figure out what the minimum value of area moment of inertia, second moment of area, is. So this gives us the minimum I would be allowed is 5 over 384 WL to the 4th over E times the maximum allowed deflection. Now we can put in numbers. I'm going to plug in numbers here so that the required second moment of area comes out in inches to the 4th power. Our inputs have a mixture of feet and inches. This is another drawback of US customary units. So we have 5 over 384, which is just a number. And then 120 pounds per foot is the load, W, per unit length. So I'm going to multiply that by 1 foot per 12 inch. So the feet will cancel out and we'll be left with pounds per inch there. So 120 pounds per foot will end up being 10 pounds per inch. And then we have 12 feet for the length, and that's going to go to the 4th power. So 12 feet times 12 inches per foot will be 144 inches for the length. So then we'll get a number in inches to the 4th power. So multiplying the numbers out, I get that we need a second moment of area of at least 82 inches to the 4th power. Since my pre-calculated table has centimeters to the 4th power instead, I multiplied that by 2.54 to the 4th power, and I get about 3,400 centimeters to the 4th power. Then we can go look at my table, and it looks like if we want 3,400 centimeters to the 4th power, a 2x8 is not good enough, but a 2x10 is just fine. So I think the joist for this row house problem will turn out to be a 2x10. The next thing we can do is check the bending stress. So we have the bending stress is bending moment times height above the neutral surface divided by the second moment of area. and this geometrical factor is pulled out and called the section modulus of the cross section. So that gives us the minimum section modulus equals the largest bending moment divided by the allowable bending stress. So this we worked out to be 2160 foot-pounds, and then Professor Farley gave us that this was 1300 pounds per square inch. And if we want to result in inches, I guess we have to multiply this numerator by 12 inches per foot, and then everything, the pounds will cancel out and we'll be left with inches cubed. So plugging in numbers, I guess so 2160 times 12 divided by 1300, I get 19.9 cubic inches for the minimum allowed section modulus. Since my table is in cubic centimeters, I multiplied that by 2.54 cubed. That's about 327 cubic centimeters. And here's my table. So it seems as if a 2 by 10 is fine. A 2 by 10 is 370. We need 327. So I think the 2 by 10 joist that we found from the deflection criterion is also just fine for this bending stress criterion. I think the third criterion that we could check if we had the right input is the shear stress. So for a rectangular beam, for a rectangular cross section, the maximum shear stress is 3/2 V over A. This is the area of the cross section. So this is 3 Vmax over 2, and this is the width times the height of the cross section. And our Vmax is WL over 2, if you remember from our shear diagram, which is 120 pounds per foot times 12 feet over 2 equals, well, that's this is just pounds per foot. Pounds per foot times foot is 720 pounds. So that's 720 pound over 2, 1.5 inch, and the height is 9.5 inch. So 2 by 10 is 1.5 inches wide and 9.5 inches tall. Okay, so we took the maximum shear from our shear diagram, which turned out to be 720 pounds. So 120 pounds per foot times 12 feet divided by 2, WL over 2, it's 720 pounds. So 1.5 times Vmax, and then divided by the area, base times height of the beam cross section. 1.5 inches times 9.5 inches. So that'll give us shear force per unit area. Plugging in numbers, that works out to be 76 pounds per square inch. And I need to check with Professor Farley, but I'm going to guess that this 85 psi value is probably what he lists as the allowable shear stress. So that's the third check, the shear stress check. So there's some allowable value, and for this rectangular beam cross section, you check whether 3/2 V over A is smaller than that allowable value. Okay, so again, it's not that we know how to do this after this course. Rather, it is that this course, with its emphasis on forces and torques and vectors, leaves you with a toolbox that has you in good shape to take Professor Farley's course in the future. Or if you're just taking this course as a sector requirement, again, you get some insight into how do the internal forces in a beam and the torques exerted by one part of a beam on another and the deflection under load and so on affect the choices that designers make for how tall a beam they need to put in the ceiling of your basement, or how big an I-beam do they need in the building you see going together down the street as you walk through Center City. Here's one last example taken from Onouye and Kane, and they gave values in US customer units, and I just converted them into SI units because I like SI units better, but we can compare with their final result. So we should get an answer similar to 24 inches, which is like 0.61 meters. So a timber floor system uses joists made of 2 by 10 dimensional lumber. Each joist spans a length of 4.27 meters, simply supported. The floor carries a load of 2,400 newtons per square meter. At what spacing should the joist be placed? In order not to exceed allowable bending stress, F bending allowed is 10,000 kilonewtons per square meter, which is 10 to the 7th newtons per square meter. So he's not asking us in this case to design for deflection. He's asking us to design for bending stress. Let's see what we get. We worked out from the previous examples, V and M diagrams, that for a simply supported beam with the uniform distributed load W and of length L, the maximum bending moment is WL squared over 8. So I think we can use that. And then we also have the bending stress is My over I, which is M over S. And we can look up for a 2 by 10 dimensional lumber, the section modulus is 370 cubic centimeters. Okay, so that's this value here. BH squared over 6 for 2 by 10 US dimensional lumber, 370 cubic centimeters. So in this case, we're basically told what cross section we're using. So that gives us, we can look up the section modulus for that cross section in a table. And we're also told what kind of material we're using. And that is 1.0 times 10 to the 7th newtons per square meter. So that tells us that the maximum bending moment that we can support is this FB allowable times the section section modulus that we're given. So those are both givens. So okay, so we have some maximum bending moment that we can tolerate. So we just multiply this number by this number. Okay, that works out to be, you have to be careful to not mix up centimeters with meters. That works out to be 3,700 Newton meters, or 3.7 kilonewton meters. Then, so that's one expression, that's the maximum allowed value of bending moment. And then here's the maximum actual value of bending moment depending on the load and the length. We're given the length, so then we have to relate this load, which is force per unit length, to the specified force per unit area, and then the spacing between adjacent beams. I guess we can do that. So let delta x be the spacing between adjacent joists. And so 2,400 newtons per square meter times delta x equals W, the force per unit length. This is force per unit area. This is spacing between adjacent beams, which is a unit of length. So then the result is force per unit length along one beam or joist. And then we can turn this equation around and write W equals 8m max over L squared, just solving for W. So then this equals 8m max over L squared. And we're trying to solve for delta x. So that gives us this delta x, the joist spacing, is 8m max over L squared times this 2,400 newtons per square meter value, which is specified up here. And I think we're going to get something that works out to be about 0.6 meters. Let's try plugging in some numbers. Plugging in numbers, I got 0.68 meters, which is of the right scale. So somehow we expected to get about 24 inches, which is about 0.61 meters. So we plugged in 3,700 Newton meters was the maximum allowed bending moment. We plugged in the length of the beam squared. The length was 4.27 meters. We plugged in 2,400 newtons per square meter was the force per unit area that the floor is designed to carry. And then let's look at Onouye's solution on the next page. He uses US customary units. So if we look at some of Onouye's intermediate calculations, he did the same multiplication of section modulus times allowable bending stress, and he got 31 kilopound inches, and I just worked out my numbers. My numbers worked out to be 32.7 kilopound inches. So that's pretty close. Okay, anyway, you can look through the rest of Onouye's solution in the slides if you want to. But again, the point was just to illustrate what people in the real world do with these V and M diagrams. So that is beyond all I have on beams.